on the applications of conceptual hydrogeology, organized by the Department of Geology with the help of Geological Institute, Presidency University, Kolkata. We are glad to inform you that we received numerous applications for this webinar, and because of this we are also live streaming the same event during the session. To start the proceedings, I would invite Professor Gautam Ghosh, Head, Department of Geology, Presidency University, to give the welcome address. Sir, the dais is for you.
Thank you, Aditya, and good morning, everybody. I welcome the speakers of today's event, Dr. Saha, Professor Sikdar, our Dean of Science, Professor Mukhopadhyay, all my colleagues, friends, and all the participating students. I welcome you all in this webinar series on behalf of Geology Department and the Geological Institute. Firstly, I must congratulate Dr. Aditya Sarkar and Dr. Utsav Ghoshal for their painstaking efforts in conducting this web series along with the help of a band of dedicated students. So, as we all know, that utilization of groundwater resource has played a key role behind development and progress of human civilization. However, overutilization of this precious resource has made it vulnerable in all scales at present, and our civilization is facing this crisis. It is therefore the need of the hour to delve deep into the science of hydrogeology and look for upkeeping and sustainable management of this essential natural resource. This can be achieved through development of manpower and scientific skills, developing societal consciousness in groundwater utilization and mitigation, and also by initiating policy-level changes and to develop a holistic groundwater quality control and management system in our country. With these things in mind, the Geology Department has organized this two-day webinar series, and today and also tomorrow we will hear from eminent scientists from different universities and institutes in this webinar who are actively involved in research on groundwater resource and management. The attending students will have an opportunity to learn beyond their normal academic curriculum through these lectures and subsequent interactions. I hope this would eventually help the students to develop themselves as professional hydrogeologists or to pursue research on applied hydrogeology in future for its better utilization in our society and for societal benefits. So with this short introduction, I would now request Dr. Sarkar to please carry on with the proceedings of today's program. Thank you. Thank you all.
Yes, Aditya sir, your microphone is turned off.
Sorry. Thank you for your kind words, sir. I would now invite Professor Joydeep Mukhopadhyay, Dean, Faculty of Natural and Mathematical Sciences, Presidency University, Kolkata, to share his thoughts with us.
Good morning, everybody. Thank you, Aditya, for giving me this opportunity to address this webinar. And this is a great privilege and honor for me to welcome you all in this webinar on behalf of our Honorable Vice Chancellor and also from all the staff members of the Presidency University. To begin with, let me remind that we are passing through a very hard time of human civilization. We all know that our life activities, regular activities, have been curtailed to a great extent, and this is affecting our students in particular from schools, colleges, and universities to a great extent. They are not being able to attend the regular classes. They are not being able to enjoy the ambience of the campus, their friends, and for months together. And this is a very grave situation. And you all know that we teachers also suffer, our hearts also bleed when our students suffer. So it was equal sufferings for all of us. But in this situation, a grave situation of challenging, a very high challenging situation, we also have some silver lining, and we develop certain technologies with the help of certain technologies, particularly the web-based technologies. We have started, the giving our lectures and courses and assignments through online teaching program, and particularly the online seminars, which we call webinars, have become very popular, and the webinars are actually cutting across the boundaries of the institutions, universities, and even states and countries, and is a very, very effective platform to share all our thoughts and our knowledges. In fact, this has given us a rare opportunity to attain to some of the topics which otherwise we would not have been able to, and to present before a very large audience, so we can spread our message very effectively. And I'm happy to share with you that the Presidency University, like all other universities, all the departments of Presidency University are actually arranging the webinars regularly. Some of the departments have also arranged the training programs, then short course programs, and I'm particularly happy to let you know that the Geology department of our university is leading ahead because the students are taking the lead. Our Geological Institute, this is the oldest student academic chapter in the country, is taking the lead in organizing the webinars in geology from our department. Not only the webinars, they are also arranging workshops, short course for students all over, the globally, and also some students quiz program. And this is really very happy moment for all of us, that the institute, Geological Institute, which was established in the 1906, in the oldest geology department of the country, that has started its journey from 1892, is really carrying all the responsibility for more than hundreds of years. The topic of today, the applications of conceptual hydrogeology, is very relevant for this department. And I must say that our young teachers and our students of the Geological Institute actually gave priority to the fundamentals and conceptual thoughts of the hydrogeology. And we have very eminent speakers and teachers among us to deliver lectures. So on behalf of the university, I welcome Professor B.V. Bhattacharya. Professor B.V. Bhattacharya is teacher of many teachers. In fact, he is a teacher of me as well. When I was a student at the undergraduate classes, I attended his lecture at Presidency College. So he's a very senior and eminent person in the field of geophysics, and in particular. Then we have Professor Shashank Shekhar from University of Delhi. Sir, we are very glad that you spare your valuable time to teach our students and share your expertise with us, and we are really grateful to you. We have Dr. Dipankar Saha. Dr. Dipankar Saha is an alumnus of this department, and he needs no introduction to the geohydrology community of our country, because he is one of the leading experts in the field of hydrogeology, and he is in the planning board of the government of India. He has carved his niche in the top level of the geological scientific fraternity of the country. And we have no other than Professor Pradeep Sikdar. Professor Pradeep Sikdar is a teacher of great admiration to his students. He has a very successful teaching career, and he supervised numerous PhD students in geohydrology, and we would be very glad to listen to him. Let me take this platform to remind you, and particularly to inform my students, that the diversification of the fundamental fields of geology into the interdisciplinary areas like geohydrology, planetary science, remote sensing, and other fields was initiated way back in the 1970s.
Sir, your mic has gone off suddenly.
Okay. Is it okay now? Hello? Aditya?
Yeah, it's okay.
Sir, we can hear you. We can hear you.
Okay.
We can hear you.
How long it was off? For a long time?
No, sir, just 1 minute.
For 15 seconds.
Okay.
Maybe.
So I was talking about Professor Saha and his contribution in the field of diversification of our fundamental geology into the fields of environmental science and geohydrology that started in the Presidency College Geology Department way back in 1970. And we all are those who were students in the last half of the 20th century, we were his students. And in fact, two of our speakers of today were associated in their early career with Professor A.K. Saha. So I find this is a very good moment for our department that our young pool of faculty is also carrying out this tradition of the department with the able guidance of our senior professors, senior teachers of the department. And it gives us an edge over other, in diversification of fundamental disciplines of earth science into areas of societal importance. And we will definitely listen today and tomorrow more technical aspects of fundamentals of hydrogeology. And I believe our basic geological knowledge is now more important, more relevant in hydrogeology, particularly in understanding the subsurface aquifer geometry, the subsurface aquifer stratigraphy, the controls on the subsurface aquifer geometry, geological controls like tectonic controls and other controls, particularly in the alluvial basins. And also we would also expect a lot of the inputs from how we can tackle the differences or diversification in exploration in different terrains, geological terrains, depending upon their bedrock geology. We will also expect that how the coastal geodynamics controlled by the sea level changes are affecting the geohydrological scenario in the coastal belt. And I would, in fact, in the coming years, coming days, in the post-COVID world, we are going to be a smart society in many ways, and many of the applications we will have based on the web applications. And in the geohydrology field, we will also expect that a lot of data will be generated from geophysical exploration, from remote sensing studies, and we will be able to integrate all this data into stochastic models, and that can be used for web-based applications like what we did in the climate science. And actually, it will be then eventually available to the common people, common users through web-based application, and we will embark on an intelligent society. So with this hope, and with a very high hope on my younger colleagues of the department, I would just thank and I would welcome all of you to this webinars, and this will be an eye-opener for our future direction. Thank you very much for giving me the opportunity, and I welcome you all once again. Thank you.
Thank you so much, sir, for these words of wisdom. So we are going to start with the first session. Our first speaker is Dr. Dipankar Saha. He is an eminent hydrogeologist who has extensively worked in the field of hydrogeology. He had been associated with Central Groundwater Board and is currently the secretary of the Indian chapter of the Indian Association of Hydrogeologists. He has always been kind to us and has always been generous enough to share his experiences with us. So, sir, I would like to invite you for the session for the first session. Thank you. Just
Thank
a
you.
second,
Thank
sir.
you, Aditya.
Just before, yes, sir. Just a minute. I would request all the attendees to keep their mics and video off during the session. Thank you. Sorry, sir. Please continue.
Okay. Can you see my slides? Can you see my slides?
Yes, sir. We can see your slides.
Yes, sir. We can see your slides. Yes, sir.
Okay. Good morning, everybody. I am thankful to the Presidency University. In our days, it was Presidency College. To invite me and share my experience in the field of groundwater and hydrogeology. So I was a student of geology, then studied hydrogeology in my MSc thesis. Of course, in those days, the structural geology, petrology, they were more glamorous. But somehow we pursued groundwater. Then we entered into Central Groundwater Board. Personally, my choice was for Central Groundwater Board, and I spent good time. And later on, I realized, and I am thankful that maybe rightfully I chose groundwater as my subject, and it has become my passion. And the most interesting thing of groundwater is that it has got it's a really multidisciplinary. Multidisciplinary means say one issue is that you are working with the many branches of the science. Like in groundwater, if you take Central Groundwater Board, there are hydrogeologists, there are a lot of engineers, there are a lot of geophysicists, there are a lot of geochemists, there are a lot of hydrometeorologists, there are hydrologists also. So it's a really multidisciplinary environment, and many a time the investigations of groundwater are the exploration of groundwater is convergence of evidence through different study you applied, and ultimately you converge into an evidence that okay, you drill a well, you will get water here. It's like that. Then as my sphere is expanding little bit, I would say at the last phase of my career, and even after my superannuation, I have superannuated in December 2017, 31st December. So now I realize that it's the multidisciplinary aspect is much bigger, much wider. I used to listen about the persons who are working in groundwater from entirely different subject. Then I started interacting with them, and I find some of the best minds in economics, some of the best minds in sociology, some of the best minds in gender equity, some of the best minds in artificial intelligence. They are also working in the domain of groundwater. So it's a really, I would say, a rocking subject. And I hope that there are many. I am told that most of you are those who are listening. They are mainly students. So my presentation, I will try to be a little bit simple and in a general approach. I will try to tell you what is the importance of groundwater in the world, what is the importance of groundwater in India, and why it is so much critical as a natural resource for the development of India, for food security, for drinking water security. And then how there are some basic idea of how the groundwater occurs and how the groundwater moves, and then how the groundwater occurs in the multi-layered aquifer system, how the groundwater occurs in the hard rock aquifer system, in the peninsular India, in the central India. So I'll try to explain all bit in a general way and try to give you a pan-India view, pan-India outlook of the groundwater occurrence, groundwater resource availability, groundwater exploration. And then at the end, I will tell you about the National Aquifer Mapping Program. That is the largest program taken up anywhere in the world on mapping the aquifers of India, because it is so important for the development of India groundwater resource. So a separate big program that has been taken up. We call it NACUM, but basically it is National Aquifer Mapping and Management Program. What is the program and what they are doing? So let us start my presentation. In the first slide, you can see a map of India. I hope you can see my cursor. This is the aquifer map of India. You know, there are many versions of aquifer maps of India put up by some researchers, put up by Central Groundwater Board at different time, even put up by some eminent researchers who are from outside India. But combining all, the Central Groundwater Board has taken a lot of pain, and they have divided India into 14 major aquifer system and 42 major aquifer system and 14 principal aquifer system. So they are the 14 principal aquifer system in India. This is the map. I will explain it on later. And this photograph is a typical exploration photograph where the rigs are deployed. They drill for well, of course, after a lot of hydrogeological investigation, geophysical investigation, a lot of interpretation of satellite imagery. We place our rig. All the groundwater investigating state and central government department, they have a lot of rigs under their department. They carry regular exploration followed by pumping tests, steel tests, a lot of testing on the aquifers. So this is a typical drilling that is going on, and fortunately a lot of water is there, and it is a typical drilling in the hard rock area, and you can see the water is gushing out when the well is under development by using compressed air. So the first slide of India to tell you again how the groundwater in India is so important. You can see the groundwater abstraction. Abstraction means groundwater extraction in India. Many of you may know that it is highest in the world. It is about 250 kilometer cube. I mean 250 billion cubic meter. Then one of the very few areas we have overtaken even China, that is in groundwater extraction. China is about 112 billion cubic meter or 112 kilometer cube. Then USA, Pakistan, Iran, Bangladesh, Mexico, Saudi Arabia, Indonesia, they are far behind. So India is the largest groundwater extractor as a country, and but the importance of groundwater is much beyond only the volume of groundwater, only the quality of groundwater. It has got tremendous cascading effect in employment generation in the rural areas. It has got tremendous effect on the livelihood of the particularly marginal and small farmers. You will not believe that you heard about the lot of suicides in the Vidarbha region or in the peninsular India, in the dry area. In many a times, hundreds of farmers commit suicide every year, and many a times the suicides are directly or indirectly linked with their wells, whether the water is coming out from the wells, whether the aquifers are drying up, and ultimately, if no water is there in their wells in the farmland of the rain-fed areas mainly, or in the peninsular India, or in such areas where canals are not there, so the farmers are helpless. Many a time they enter into the debt trap, and ultimately they commit suicide. So the importance of groundwater in India, if you see the socio-economic arena, it's a very wide and very, I would say, very penetrating effect of groundwater in the socio-economy of India. A little bit about how groundwater is utilized in the different countries of the world. Of course, in this map, some of the countries, the groundwater data is not sufficient. But you can see that the red means the more intense groundwater development. And you can see that India is the front runner in intense groundwater extraction in the entire world. Of course, in USA is a lot of groundwater extraction is there, in Europe also. And you can see again in China, lot of groundwater extraction is there, particularly from their alluvial valleys and the deltaic region. But there is no comparison of the dependence on groundwater resources in India. You will not get any comparison anywhere in the world. Now you see the India is covering. India is having only 4% of the world freshwater resource, but inhabited by 18% of global population. So naturally, if you see water as a whole, surface water, groundwater, both, so it's a big challenge. A lot of population, but the proportionately less water resource is available in India. The average annual groundwater resource, average annual water resource potential of India is 1,999 billion cubic meter. This is average annual water resource potential. This is surface and groundwater together, of which the utilizable resource is 1123 billion cubic meter, 1,123 billion cubic meter. That is the utilizable resource. That resource is available every year. It's generated every year. You know, India is blessed with a very good monsoon season. Every year the monsoon comes. They bring a lot of fresh water over the landmass. So they are available on rivers, they are available on dams, and they penetrate also underground and recharge the groundwater. So the utilizable resource, 1,123 billion cubic meter, means that annually this water is available, and this volume of water we can utilize for our societal use. So out of 1,123 billion cubic meters, 690 billion cubic meter is from surface water, and 433 billion cubic meter from groundwater. Now, see, 433 billion cubic meter of groundwater means that about 430 billion cubic meter water is recharged every year. But please remember that a major part of the recharge is from rainfall, of course, as I told you. But beside rainfall, there are other sources of recharge, like return seepage from the agricultural field. You know, large part of India is still use flood irrigation. So about 25% of the water that you spread on the field, it goes down and recharge groundwater. Then seepage from canal, then seepage from tanks, then seepage from water harvesting artificial recharge structures. So recharge from all sources in a year is 433 billion cubic meter. And 690 billion cubic meter of surface water is that the surface water that is available in dam, that is available in rivers, that is available in different type of reservoirs. But also it includes that water which is supposed to be stored in the dams which are under construction also. So 690 plus 433 billion cubic meter. 433 billion cubic meter of groundwater recharge, it varies year to year, because you know a major part is from rainfall. So if rainfall is more, the recharge is more. If rainfall is less, the recharge is less. It's like that. So about total extraction of water, you see groundwater and surface water total, it's about 710 billion cubic meter, a little bit old data. And irrigation is the major user of groundwater. So, major user of water as a total, and irrigation consumes 90% of the groundwater extraction. But if you consider the surface water and groundwater together, then about 77% of total water is used by irrigation. Then in 2050, the total withdrawal, the total demand will be 1180 billion cubic meter. And by that time, the irrigation will account about 68%. So it will come down from presently 77% to 68%. Again, I repeat, it is a total water demand, surface water and groundwater both. You know, a lot of areas are under canal command also. So now the issue is that we are from where we will get 1180 billion cubic meter of water, because our utilizable resource is only 1123. So we are heading towards a very tough water scarce situation in India. So if you see the increasing demand for water for various purposes, so you can see that the irrigation will continue. Irrigation will continue to dominate. There are three bar diagrams are there: 2010, 2025, and 2050. And you can see the green color is the demand for irrigation. So always the irrigation was the major consumer of water, surface water, groundwater together. And even 2050, we need 807 billion cubic meter of water for irrigation. There will be a lot of improvement in the irrigation efficiency by use of smart irrigation like drips, like sprinkler, like laser leveling, like there are many other ways. So even crop diversification, but still we need 807 billion cubic meter of water. And then at the top of the graph, you can see the drinking water is 111 billion cubic meter, then 81 is industry, then we need a lot of water for energy, particularly our power plant, and then for others also like recreation, many things. So it's a very tough days ahead, I will say, for India. The annual water availability is 1123. I told you that it is annual recharge, and the demand will be 1180. But this is a lump model for the entire India. If you see, I will show you some slides that in many, about the 20% of India, already there is a huge scarcity of water. We have entered into that phase. Now to say a little bit about groundwater, that how important it is, it caters 64% of our irrigation needs. And remember, I reiterate that in spite of our huge investment on dams, huge investment of our canals, and huge euphoria about the big surface water reservoirs, still the groundwater is silently serving the Indian nation. 64% of our irrigation needs are from groundwater, and they are through wells. And remember, there is a very interesting aspect of that. If you see the socio-economic aspect, they are all through private investment. There is no government, say thousands of crore rupees of dams governments are not building for groundwater. So it's all well owners' money. The small landowner, the bigger landowner, everybody has got their own well. They put their money, they maintain their well, and they take out water to irrigate their land. And as per the latest census of Government of India, about 22 million wells are working for irrigation. I repeat, 22 million wells are working for irrigation. It is unprecedented in the entire world, and that's why many economists use the term atomistic development of groundwater. So 64% of our irrigation needs, 85% of our rural drinking needs, 50% of our urban water needs. When the water comes in your tap, so you always have a mind that you might be coming from some reservoir. So if you open a tap in Mumbai, you feel that it is coming from a reservoir. Yes, it is coming from reservoir. But if you open a tap in Delhi, don't feel that the entire water is coming from a reservoir or from a canal. There is a huge floodplain groundwater development in the northern part of Delhi, from where a major part of the water supply is coming and substantiating the water supply in Delhi. Now you go to any town in the Indo-Gangetic plain, in the Indus plain, you will find that the entire water of the huge urban areas entirely dependent on groundwater. So as a total in India, 50% of the urban water need is from groundwater. And the interesting is, whatever irrigation is expanding, they are expanding at the cost of groundwater. If you see the last 4-decade data, more than 80% of the increased irrigated area is scattered by groundwater. So I'm trying to give you a wider picture how the groundwater is serving the nation in water supply, in industry, in irrigation, everywhere. About, I told you that 90% of total groundwater extracted in India is used for irrigation. And you will not believe that the contribution of groundwater to India's GDP is about 10%. 10% of gross domestic product of India is contributed by groundwater. There are brilliant economists in India. They are working on groundwater economics, and their researches has indicated that how the groundwater is performing. If you consider simply its economic value, the economic value of groundwater extracted in India is about 8 billion US dollar, and the groundwater based irrigation economy, it's bit old data, but I could not find any latest data, but it's about 60 billion US dollar. You know, when you use groundwater for irrigation, I told you that there are other effects, cascading effects. There are employment generation, there are spreading of the rural electrification, there are spreading of the mechanics who repair pumps, who repair tubes. Millions of jobs are created. So the groundwater-based irrigation economy in India is 60 billion US dollar, and presently I am sure it is much more than this. Now, to start with the technicalities of groundwater, to make it a bit simple, I will say that broadly there are two types of aquifers. Those who are absolutely new for groundwater, I would say that the aquifers are the geological layers, geological rocks where groundwater is stored. And also the groundwater can move. It is not that the groundwater is only stored in the rocks. It must move, and it must come to the well also, where you are drilling a well. Then only the water will come out in your well. So the two basic properties are required, that water will be stored in the rock and water can move through the intergranular spaces or through the fractures or fissures in the rock. Then only you will tell a formation an aquifer. Then there are other aspect of this that in the definition you can find in your subject book, that the water should come out in an economic volume, in a cost benefit manner. But this economic volume, cost benefit manner, they are all relative question. You know, if you are in West Bengal, or if you are in the Indo-Gangetic plain, if your total dissolved solid is say more than 500 milligram per liter, you will be annoyed. So you will be cursing the water supply department. ये क्या पानी दे रहा है हमको? It's a saline water. It's a brackish water. Tasty, salty. But if you go to Rajasthan, I worked about a year as an advisor to the government of Gujarat, and I worked extensively in the areas of Kutch. There, even the TDS is 2,500 milligram per liter, the people are happy. They enjoy that. Okay, the good water has come. So those things are relative, that the volume of water should be economically in a cost benefit way, or the quality of water. It depends on at what level the water scarcity is. But the aquifer, if we come back again, two basic properties: water should be there, and water should be able to move. Now there are two broad types. One is soft rock, one is hard rock. Now soft rock means the loose, unconsolidated sand, silt, clay, etc. They are the soft rock. And you will get in the Pleistocene deposits, Holocene deposits, in the vast Indo-Ganga Brahmaputra plain, and also in the deltaic region, also in the valleys of, say, Narmada, in the valleys of Mahanadi, in the valleys of Godavari, wherever the valley fill deposits are there, alluvial deposits are there. So you will get the soft rock. Now in the soft rock, the sands are the aquifers, because you can see this figure. This is a sand grains under the microscope. So the sands these are the yellow colors of the sand grains, and they are the intergranular space, and the groundwater moves through the intergranular space easily. It moves, and it moves in all directions. So we call it isotropic. So wherever you put a well, this is well number 1, this is well number 2, wherever you put a well, you will get water. But you will get water from the sand layers. Say there are clay layers also, there are silt layer also, there are sandy clay layers also. You will not get water from those layers, though there are a lot of water within the clay. The reason is the water cannot move. So wherever there are sand layers, in a simple way, clay or pebble layers or gravel layer, you will get lot of water. And whenever you drill a well, wherever you drill a well, you will get water because it is isotropically distributed. It's a picture of heli-borne electromagnetic survey of the Gangetic Plains. Here the yellow and the red colors layers are the sand layers, and the green color layers are the clay layers. So at the top you can find a clay layer about 10 to 20 meter thick. Then you find a sand layer, and red means coarse sand, yellow means fine sand, red means coarse sand. Say about 30 meter thick sand layer. Then again you will get a clay layer. You can see the green color. Then below that you get a quite thick, about 70-80 meter thick sand layer, and it's a major part of the sand layer is coarse sand. So in the alluvial areas, in the deltaic areas, you will get sand clay alteration, and wherever the sand layers are there, they form the aquifers. Now let us go to a little bit more complicated scenario. Say in the alluvial areas where the Pleistocene deposits are there, Holocene deposits are there, you will get multi-layered aquifer system. So I told you always, wherever the sand are there, sand layers that form aquifer, but they alternate with clay layers. So if you drill wells and you collect the lithological logs, so you can see how the sand layers are extending from one place to another place. You see the left side, this is a panel diagram we call, and they are the location of the wells. So in different wells, you prepare lithological logs. The sand layer, then clay, then sand, then clay, then sand, then clay, something like that. So up to 300 meter by and large, our exploration goes on in the Indo-Ganga-Brahmaputra plain. So within the 300 meter, we generally get 2 to 3 aquifer system. And the 3 aquifer system, they are, it's not from say 50 kilometer or 100 kilometer extension. They may change into 2 aquifer system, they may change into 4 aquifer system as you are going laterally because of the constant phases variation. Now, a typical example from the middle Ganga plain, Bihar, bordering UP, you see there is a typical 3 aquifer system. At the top, you see my cursor, follow my cursor. At the top, there is an aquifer system, very good aquifer, made up of sand. This blue color is sand, yellow color is clay. This is, from this aquifer, there is limited extraction because this is arsenic contaminated. And from the left-hand side, you can see the depth, 0 to 280 meter. Now, after this clay layer, there is aquifer 2. This aquifer 2 is intensively exploited in the urban areas, as well as nowadays the exploitation is increasing for the agriculture purpose. Below that, there is again a clay, and the third layer is again aquifer 3. Aquifer 3, though it is highly potential, it is hardly getting exploited because a lot of water is already there in aquifer 1 and aquifer 2. Now, my point is, it is very, very important to understand the multi-layerity of the aquifer, their hydraulics, their hydraulic head behavior. I mean, each aquifer has got different hydraulic properties. Each aquifer has got different hydraulic heads or water levels. So we must understand this because of various reasons. I give you a simple example that the aquifer 1 is arsenic contaminated, but the aquifer 2 is not, aquifer 3 is not. And you see here, the aquifer 2 is highly, highly exploited. So when you plan for an artificial recharge, you have to recharge the aquifer 2, not aquifer 1. If you put a recharge structure targeting aquifer 1, there will be simple waterlogging. So because of various reasons, you have to understand the different aquifer system in the alluvial plain, in the deltaic region, in the valley field region, wherever the soft rocks are there. Now come to hard rock area. Broadly, I told you there are 2 types. In hard rock, they occur in the top weathered zone. You are all geology students, you know there is a weathered zone, 10 meter, 20 meter, at places it can go even up to 30 meter thick at the top. They are soft rock. where the groundwater occurs within the intergranular spaces. But the interesting story lies below the weather zone within the hard rock. You can see my cursor, these are the fractures, and the fractures are unevenly distributed, anisotropically distributed, and groundwater occurs and moves along the fracture. So that gives an anisotropy in the aquifers. So if you see my cursor, this PZ10, so this well is drilled up to 450, no, it is above mean sea level. So this well, you can say, drill up to 200 meter below ground, but not a single drop of water has come out from the well because the entire hard rock part is devoid of fracture. So there is no fracture, no water. But see this PZ3, this well is about 150 meter deep, and they are encountering a lot of fractures. So it gets a lot of water into the well. Now you come to PZ8, come to these wells, up to say 180 meter below ground or so, there is no fracture. So the well was dry, but never lose your heart. You should go on drilling in the hard rock area as per the data that you have inferred from your geophysical study. And you see, after crossing 180 meter or so, lot of fractures are there and lot of water has come out from the well. So the groundwater occurrence and movement, it behaves in a different way in the hard rock area than in the soft rock area. And these small wells, if you see my cursor, they are dug wells. The dug wells take out water from the weather zone. And I told you the weather zones are 10 meter or 20 meter thick in general. But I tell you that in most part of India, the weather zone becomes completely dry nowadays because of the heavy lowering of water level in the hard rock areas. And if you see on the left hand side, these are the drilling, and the blue lines are the fracture zones. Say in this well, you tapped 1, 2, 3, 4 set fracture, and the discharge of the individual fracture sets are given. 1.2 liter per second, 0.6 liter per second. So this well is lucky. But you see the piezometer 12, there is no water up to 185 meter below ground. So it is completely dry well. In piezometer 4, there are 2 fractures are encountered, 4 liter per second, 31 liter per second, very good water. So it's water is there. So it's like that in the hard rock area. Now it's a photograph of the hard rock area. These are the fractures. You all know, geology students, that in these fractures the groundwater occurs, and these photographs will tell you the weather zone at the top and the fresh rock at the bottom. You can see my cursor. So in the fresh rock part, the water occurs in the fracture, and in the weather zone, the groundwater occurs, and we take out that water through our dug wells. Now, if we come to the water level, the water levels are intricately tied up with the monsoon in India. So water level are, as the monsoon comes, as the rainfall starts, the water level starts climbing up and climbing up. And as the monsoon recedes, then it is going down and down. But if you see the well hydrograph, it's a typical 1-year well hydrograph. May is the deepest water level because it is the pre-monsoon period. There is a sharp rise in the water level. Then there is a fall in the water level. Sharp rise in water level in the month of August is the peak monsoon period. Then there is a fall. There is a steep fall till the month of November. This is an average water level behavior throughout India. And after November, the water level gradually falls down till the month of May or till the onset of next monsoon. So we measure water level in the month of May, we measure water level in the month of August, that is mid-monsoon, then in the month of November, that is post-monsoon, and again in the month of May. But we also measure in between in the month of January. So this is the standard water level measuring protocol in India. So the November water level we call post-monsoon, and November is the month when the massive groundwater exploitation for irrigation for Rabi crop starts, and it continues up to May. So between the month of November and between the month of May, what is the groundwater available? Volumetrically, we call it replenishable groundwater resource, because that resource is mainly used for our societal use and for irrigation. And I told you that 90% of our, more than 90% of our groundwater extraction is used for irrigation. Now, this is the brief idea of how the rainfall varies. You know, the monsoon comes from Bay of Bengal and enters from West Bengal, Bangladesh, northeastern region, and moves westward. And as it goes west and west, the rainfall diminishes and diminishes. Rainfall reduces and reduces. And you can see it is 100, say 200, 300 millimeter centimeter per year in the West Bengal, in Jharkhand, Bihar, and gradually as you are going west and towards west and northwest, it is reducing and reducing and reducing. And in the desert of Rajasthan, in Jaisalmer, it's not more than 200 or 150 millimeter per year. The same is the case in the Gujarat, in the area of Kutch, in part of Punjab. We all know they are the arid areas bordered by semi-arid areas, but the eastern part and central part is blessed with a good amount of rainfall, and that is one of the reasons that a lot of groundwater recharge is also taking place. But at the same time, I will tell you the intensity of groundwater development is also less in the eastern part because of various reasons. I'm not going into that. And these are the location of the groundwater monitoring wells. There are many wells in India. Say about 24,000 wells are being monitored by Central Groundwater Board. And in addition to that, more than 1 lakh wells are monitored by the state governments. So if you plot all the wells, so it's look like that. So there are many wells, and the water level from these wells are used for preparing the depth water level map. This is the left-hand side is the post-monsoon water level map in the month of November. This is the pre-monsoon water level map in the month of May, end May or June first week. And this is, I will say, more focus on the shallow aquifer system. I told you that particularly in the Indo-Ganga-Brahmaputra plain, there are multi-aquifer system. And in the hard rock areas also, interestingly, in many areas, you will find 2 aquifer system. The groundwater in the deeper fractured zone in many parts occur under semi-confined condition. So they are not exactly very well hydraulically connected with the shallow weathered zone. But this map will give you an idea of how the water level behaves in the shallow aquifer system. And till now, the major extraction of groundwater in India, the dominant extraction of groundwater in India is from shallow aquifer system. So as if you see the pre-monsoon water level, as you are going towards from the east to west and northwest, the water level is going deeper and deeper. 5 to 10 meter is the yellow area, 5 to 10 meter below ground. And in the Rajasthan, in Haryana, in Gujarat, there the water level is more than 40 meter, and their multi-layered aquifer system doesn't exist in many part. So in many areas, the water level has gone down even more than 80 meter, 90 meter, 100 meter below ground. I have recently seen in the Kutch area of Gujarat, the water level is 600 feet, say 180 to 200 meter below ground. And when they put a well in, say, pump in that, it further goes another 20, 25, 30 meter as drawdown. So you can imagine what is the pumping water level. So very deep water levels exist in those areas. And I was telling about Kutch, they are exactly multi-layered aquifer systems are not there. So top to bottom, it's a majority a single aquifer system, thick single aquifer system. So this is the water level behavior. And in the post-monsoon period, the water level comes up because of the heavy recharge. You can see the water level has come up in the central part, in the eastern part, 2 to 5 meter or less than 2 meter in many parts of India, in the North Bihar plain, in Assam, particularly in the hard rock areas also. But in the western and northwestern part, where the deep water levels are there, there is hardly any net groundwater recharge in the monsoon month because of the heavy extraction of groundwater round the year, round the clock. Now, give an idea of how the depth to water level map, if you see focus in a small area. This is an example of a marginal alluvial areas of I would say Bihar Jharkhand border. Say this area is characterized by two aquifer system. It's a shallow aquifer about 30 to 40 meter. Then there is a clay layer. Then there is a deeper aquifer about 100 meter below ground. And most of the areas below 100 meter, you will get the bedrock. Now, during the post-monsoon period, you can see the red contour represent the shallow aquifer water, deep aquifer water level. Sorry, the red is deep aquifer water level and the blue is shallow aquifer water level. So this is 3 meter below ground. This is 3 meter below ground. Deep aquifer water level here, you can see my cursor, you follow 3 meter below ground. Then again, the shallow blue contour is shallow aquifer water level, it is 3 meter below ground. I mean to say, during post-monsoon period, when the aquifers are recharged from rainfall, the hydraulic head of the shallow aquifer and deeper aquifer remains almost in same depth. But as the monsoon withdraws, there is more extraction from the deeper aquifer. So what is happening? The shallow aquifer water level remains as it is or slightly going down, but the deeper aquifer water level goes very fast. Now you see what is happening. The red color are again deep aquifer water level. It is pre-monsoon situation. It has gone down to 10 meter, 12 meter, 14 meter below ground because of the heavy extraction. But the shallow aquifer, the blue color contour, you can see 5 meter, 6 meter. So the shallow aquifer water level has gone down from 3 to 5 meter, but the deeper aquifer water level has gone down from 3 to 14 meter below ground. So you can understand that how differently the different aquifer behaves. Now this is depth to water level map. I mean at what depth the water level occurs. Now if you see, I told you that the water level is always on the movement. You are a geology student, you will understand. It moves from high potential to low potential, from higher energy to lower energy, higher elevation to lower elevation. So this is the water level contour map of the deeper aquifer. Now from the base of the hills, it follows towards the north, towards the northeast. This is 60 meter above mean sea level, 58 meter above mean sea level. You see my cursor. This is 48 meter above mean sea level. So water level follows smoothly, following the gradient. But the complexity comes here when it comes at the north of a place called Bihar Sharif. I told you from the depth to water level map, here the water level of the deeper aquifers are deeper. So what is happening in the groundwater flow regime? The Ganga is flowing at the north from west to east. The groundwater flow is towards north, but because of the heavy extraction of groundwater, a depression has been formed in this area. So from all around, the groundwater flow is converging around Bihar Sharif because of the heavy extraction. So you need to understand depth to water level map. You need to understand groundwater flow map also. And nowadays, because of the complexities of the extraction of groundwater from different aquifer systems, so you need to understand the groundwater flow regime of the different aquifers also. Now, the unplanned and reckless exploitation of groundwater, I will tell about this. It is happening in many parts of India, and we must strive for sustainable use of groundwater. So what is happening? Mainly there are two aspects. One is overexploitation of groundwater resources. Overexploitation means we are exploiting more than recharge in an annual scale. Our expenditure is more than our say salary from our bank account. Then large area under geogenic contamination. These two are main, say I would say the effect of reckless exploitation of groundwater. Many researchers are telling that the overexploitation of groundwater is triggering under various geogenic contamination. Many experts they don't agree, but many of the experts agrees also. Now the overexploitation have many collateral damage also. First of all, there will be decline of water level. The water level goes down, and you can imagine with 1 meter of water level is going down and 22 million of wells are working in India, what will be the impact on the energy cost? You know, the 80%, 85% of our pumps are working on electricity. And in most of the states, the electricities are highly subsidized or free. So you can imagine the impact on economy. Then it can happen that the entire aquifer has become dry. There are evidences on that. Then there are de-wielding yield of wells. When you will be a practitioner hydrogeologist, you will find that the water level has gone down. It is okay. But still the water level you can measure. But what is happening? When you run the pump, it will work for 3 hours. Then you have to stop the pump. Again, the water will come. Then you run the pump. So it's we call it sustainability in yield. That is also reducing. Then the river flow reduces and adverse effect on wetland. So there are a lot of discussion nowadays on wetland. But we must remember that the wetlands, they thrive and they sustain on groundwater seepage. So a lowering of water level has a tremendous impact on wasteland and river flow. Then seawater ingress in the coastal areas. I think all of you know, as you extract fresh groundwater in the coastal areas, there is a delicate balance between the saline water from the sea, which try to enter into the fresh water, and the fresh water from the land, which try to push the saline into the sea. If the delicate balance is disturbed, a lot of bad thing happens. Then groundwater sink around the urban areas, land subsidence also takes place. It is also reported from Calcutta. Now I was telling about the decline of water level. So the decline of water level will not come out from a year water level measurement. In a well hydrograph, the shallow and deeper water level follow the season. But if you plot the water level for about 20 years, 10 years, 30 years, then only you will be able to tell whether the aquifer is under bad condition or under good condition. And got a best fit line. If the line is declining, that you can realize that there is an alarm bell. The water level is permanently declining. The groundwater mining is taking place. The permanent aquifer desaturation is taking place. This is a typical example from Nakhatrana. You can see between 2001 to 2017, the water level has gone down from about 40 meter to about 90 meter below ground. You can imagine the per meter water level drop. So this is a typical example, and you can get lakhs of examples from different parts of India, the declining water level, from Karnataka, from Tamil Nadu, from Telangana, Punjab, Haryana, Maharashtra, Rajasthan, Gujarat, everywhere. Now, this is a map of India where the declining water levels are more intense and more concentrated. The shaded areas, you see my cursor, they are the areas where the water level decline are more profound, more concentrated, and many of the wells you will notice water level decline. So the groundwater resource situation is really serious in these areas. Now the groundwater overexploitation is highlighted throughout the world, and by international researchers, the groundwater overexploitation in the state of Punjab, Haryana, and Western Rajasthan has been demarcated as one of the most 3 intensively groundwater exploited region of the world. So you can see the northwestern India, then California Central Valley, then northern China province. So northwestern India, I think they are the topper between 2003 and 2012. You can see the net loss is 20 plus minus 7 kilometer cube per year. That is the net loss of groundwater. But you see the beauty, the groundwater is going down, and at the same time, what is the major crop in Punjab and Haryana? The major crop is paddy, the major crop is basmati and wheat. And we are exporting paddy, exporting wheat hugely from Punjab and Haryana to other states and in international different countries. So actually we are exporting water through our crops from these areas which are highly overexploited. So this is a really challenge for the policymakers in our country how to combat this. But there are other issues on groundwater management. I must tell you that situation is not that gloomy everywhere. And first of all, large areas under geogenic contamination, I told you, fluoride, arsenic, salinity, iron, nitrate, many. Then there is an issue of underutilization of groundwater in the eastern states also. We have realized that we can use, there are underutilized groundwater, and we can use this to usher in another green revolution in the eastern part of India. And another issue is the waterlogging and soil salinity problem, particularly in the canal command area. Then a very important issue is climate change impact on groundwater. Because of the climate change, extreme events are happening, and the rainfall is concentrated in a short period. And because of that, there is a less recharge in groundwater. There is a huge impact in the millions of springs in the hills. There is a huge impact in the recharge of the aquifers in the hard rock areas, in the valley fields, in the deltaic region. And then there is an issue of anthropogenic contamination from the industries, from the agricultures, etc. So these are the different issues of groundwater. This is a picture from the North UP plain, that in the very shallow level, there is plenty of groundwater is available, unutilized and unexplored. Now to tell you about the groundwater resource estimation. So I told you that there is an annual recharge of groundwater that we call replenishable groundwater resource, because it is replenished every year. So we call it dynamic resource also. But below that, there is a static resource. Now, if you go to, say, the Sharda depression or Gandak depression in the Gangetic plain in the state of Bihar and UP, the soft or unconsolidated aquifer may continue up to 1.5 kilometer. So up to 1.5 kilometer, huge groundwater, a part of that is of course saline, is stored in the aquifer, 1.5 kilometer or even more. But our exploitation is only within top 200 meter. And our dynamic resource or replenishable resource is confined between the pre-monsoon and post-monsoon water level, maybe within the top 20 meter. Now you can imagine from 20 meter to 1.5 kilometer below ground, a huge groundwater resource is available within the unconsolidated aquifer. So that we call static resource. So in the top, there is a replenishable resource, which is recharged every year. And in the deeper part, there is a static resource. In hard rock areas also, the replenishable resources are there. In the deeper fracture, the static resources are there. Now the replenishable resource, we estimate the annual groundwater recharge, and we minus the annual groundwater drop, we get our replenishable resource. So this is a simple expression of the dynamic and in storage groundwater resource in the soft rock area, where multi-layered aquifers are there. This is our November water level, this is pre-monsoon water level, and in between this water level, whatever resource is available, that we call dynamic resource or replenishable resource. But below that, this is static resource. Static resource in the phreatic aquifer or shallow aquifer. Now, the static resource in the deeper aquifer, you can follow my cursor, below the clay bed, again another aquifer is there. That water is not being tapped. So it has recharged maybe 100 years ago, 1000 years ago. So that is remained as a static resource. We are exploiting from the replenishable resource at the top. So this is a graphical representation of the dynamic resource. Now the dynamic and in storage or static resource in the hard rock area. I told you this is the weathered zone at the top. You follow my cursor, and the fractures, and you can see the blue color, they are water in the fracture. Now this is the November water level at the top and May water level at the below. So between this, it is dynamic resource, and below that, within the weathered zone, if some water is there below the May water level, that is we call static or in storage resource. And below that again in the fracture, whatever water is there, that we call in storage resource, because it was recharged earlier and it is lying at depth. So I think now your static and dynamic resources are explained. Hello, could you
please switch off the mic for...
Please switch off the mic. Now, it's a very, very important parameter you must understand if you are working with groundwater, that is stage of groundwater development. I mean, internationally, it is not very used in many countries, but I would say with a lot of confidence that in India, we work out the groundwater resource in a way very few countries in the world work out in a robust way that we are working out in India. The reason is many of the government policies, many of the fund disbursement, many of the regulation for the industries, many of the thousands of crores of rupees that we are investing on artificial recharge through Manrega are tied up with the stage of groundwater development. That's why our resource assessment is very robust and we have a lot of confidence on our assessment of groundwater replenishable resource, that is recharge every year. But the resource assessment boils down to a parameter that we call stage of groundwater development, and it is very easy. How much you are extracting divided how much volume of water is getting recharged every year. So multiplied by 100 is your stage of groundwater development. So if your stage of development is 60, so you are utilizing 60% of total groundwater recharged every year. But interestingly, if you go to Kurukshetra district of say Haryana, the stage of groundwater development is 263%. That means their extraction is 2.63%, 2.63 times of the recharge. So you will ask me from where the water is coming. So their recharge is 100 and their extracting is 263. So that water is coming from the static resource. Those static resources are like fixed deposits. So gradually we are eating up the static resource and ultimately one day the entire aquifer will be exhausted and we will live on the dynamic resource because hopefully rainfall will be there and recharge will be there. So dynamic resource will continue, but aquifer can become dry. Anyway, the stage of groundwater development is very, very important. As a whole, the stage of groundwater development for entire India is about 62%. Now, this map tells you the annually replenishable water resource of India. You can see the stage of groundwater development in the region 0 to 30%, 30 to 50, 50 to 70%, and at the top, the red, the alarm red is where stage of groundwater development is more than 100%. Now you can see almost entire Punjab, entire Haryana, entire Rajasthan, large part of Gujarat, major part of Karnataka, Tamil Nadu, Maharashtra, the stage of groundwater development either more than 100% or more than 90%. More than 90% we call critical. And in the eastern part, the stage of groundwater development you can find 30%, 40%. In Brahmaputra plain, lot of groundwater is there, very low stage of groundwater development, 0 to 30%. So a lot of scope is there still for development of groundwater. Now, the overexploited areas are, see, the regular groundwater resource assessment is made. It's a huge task, mammoth task. Central Groundwater Board along with the State Groundwater Department, they do it. About 6,800 blocks in the entire India. So if you see the 2004 assessment, 2009 assessment, 2011, 2013, and latest 2017 assessment, the overexploited blocks are not improving. They are there in the northwestern part of India, and they are expanding in the rocky areas in the southern part and the central part. And as per the latest resource estimation 2017, about 17% of the blocks are overexploited and about 5% of the blocks are critical, where stage of groundwater development is more than 90%. So as a whole, 20 to 22% of the area of India, volumetrically, the groundwater resource is in a critical situation. Now, a few words about the quality. The quality, see, when we discuss about groundwater, we discuss a lot about the volume of groundwater that is available, that is scarce, but the quality is becoming a major issue. You know, now a very high-level committee has been formed under Ministry of Water Resources, now Ministry of Jal Shakti, for development a water policy. So they have realized that the quality has become as important issue as volume in India now. We cannot now ignore just putting some measures here and there, putting some money in public health engineering department, on water supply department of the state, that you take some measures, some arsenic is there, some fluoride is there. Nationally, we must recognize and we must understand that quality is a major issue, and our policy should also be focused on groundwater quality as important way as volume, as quantity. Now the major, I will say, the salinity, iron, nitrate, fluoride, arsenic, but there are a lot of trace element, heavy metal concentration also that surfaces of different publication. Excellent work is going on by different research institute, by academic institute, by different state and central government departments also. So a lot of uraniums are getting reported, a lot of cadmium, a lot of chromium, but I would say they are local. Regionally, if you see the major issues, I would say the nitrate, fluoride, and arsenic, and of course salinity. Salinity means inland salinity. So to give you a simple idea of how the contaminations are distributed in India, the salinity distribution, if you see, I would say this is inland salinity. I mean, they are either old seawater remained entrapped into the aquifer, or they have developed salinity because of the prolonged rock-water interaction. They are profoundly present in the state of Haryana, in the state of Rajasthan, in the state of Gujarat, and again in the southern part of India, and they are in the coastal areas. But in coastal areas, they are, I would say, localized. They may enter into 2 kilometer, 5 kilometer, 8 kilometer, 10 kilometer from the coastal areas landward. But they are covering in the inland areas for thousands of squares of kilometer in the state of Rajasthan, Gujarat, Tamil Nadu, Karnataka, Haryana, in this state. So it's a big problem. But nowadays, salinity is also a resource. Saline groundwater is also a resource, and many industries are also trying to utilize it. And if you try to utilize the saline groundwater in the state of, say, Rajasthan or Gujarat, it is not like that you can just drill a well and take out the water. You have to take permission from Central Groundwater Authority, even for the use of saline groundwater. But saline groundwater is a problem. And what is happening because of the water level lowering, desaturation of aquifer, deepening of water level, there is upwelling of saline water in many parts of India, and the salinity is gradually increasing. I mean to say, those aquifers which used to yield fresh water maybe 2 decades back, now they are yielding partly brackish water because of the heavy overexploitation. Now, if you see the fluoride, they are also distributed in pan-India. You can say its contamination is much more pervasive. There are many researchers, they are working excellently in fluoride contamination, but this will give you an overall idea that how the fluoride contamination is distributed in the desert, in the high rainfall area, in the soft rock aquifer, in the hard rock aquifer. So it is a pervasive and all India contamination, the fluoride contamination, and you know its limit 1.5 milligram per liter, and they are really a very serious water supply issue particularly in rural water supply, which is depending on groundwater. Then there is nitrate. High nitrate is another issue. I say you can see in the map that this is most pervasive. We say that the nitrate comes from the overuse of fertilizer, but there are evidences that nitrate comes from the rocks also through rock-water interaction. But pervasive nitrate is coming from the return seepage of water from the agriculture field, and we are generously using nitrate fertilizer in the agriculture field to enhance our crop field. That is one of the reasons that the nitrate contamination more than 45 milligram per liter, you will get almost everywhere, pan India, in different rock types, but mostly they are confined in the shallow aquifer system. I would say where multi-layered aquifer systems are there, the clay layers are protecting the nitrate contamination to go below. If I little bit come back to in our previous slide, the fluoride contamination, I would say we have a lot of fluoride contamination investigation along with depth through the deep bore wells, deep piezometer drilling. The fluoride you will get in the weather zone, the fluoride you will get in the shallow fracture zone, the fluoride you will get in the deeper fracture zone also, because it comes from the rock water interaction. So wherever the fluoride bearing minerals are there, they comes into the groundwater. So fluoride has got by and large no depth control, and that is it is more problematic to tackle the fluoride contamination and provide aquifer based water supply in the fluoride contaminated area. But nitrate, I told you that it is mostly confined in the shallow aquifer system because it is seeping from the surface from the over-utilization of fertilizer. Now there are, when I come to the principal aquifer system and 42, our major aquifer system, I told you that Central Groundwater Board has classified by combining all aspects of, are combining many literature, many reports, many aquifer classifications, and finally it is concluded that there are 42 major aquifer systems and 14 principal aquifer systems in India. These aquifer systems are of course wedded with the geology because groundwater is intricately tied up with the geology, with the rock type of the area. So it is basically tied up with the geology, but there are other hydraulic considerations also. So 42 major aquifer system and 14 principal aquifer system. You can see the very important principal aquifer system is the alluvium. You follow my cursor. It is from west to east, but the alluvium in the Rajasthan, they are aeolian deposits also. They are loose, unconsolidated, but they are aeolian deposits. But the famous Indo-Ganga Brahmaputra alluvium starts from Punjab, then enters into Haryana, then Uttar Pradesh, then Bihar, then West Bengal and Bangladesh, and enters into Assam. And this forms one of the most prolific aquifer system and most extensively exploited aquifer system in the world. The next important aquifer system I will tell individually is a very interesting basalt aquifer. This light blue color is the basalt aquifer. You can see it's very important, and I am fortunate that I got the opportunity to work about 4 years in the basaltic aquifer system in Maharashtra. Interestingly, they behave like an alluvial aquifer system because of their layered nature. They are hard rock, but they behave like a layered nature because of the vesicular basalt, massive basalt, vesicular basalt, massive basalt alteration. And you will get, interestingly, artesian wells also in the basaltic aquifer. Anyway, besides that, there are various type of hard rock aquifers. There are quartzite aquifers, there are limestone aquifers, there are laterite aquifers. Those who have a particular interest, he can log into the website of Central Groundwater Board and download the Aquifer Atlas and see it. Now I told you that to map the aquifer system in a three-dimensional environment, the government of India started an ambitious program, National Aquifer Mapping and Management Program. You know, previously when we joined the Central Groundwater Board, then we were sent to field. So immediately I was posted to Guwahati. Then from Guwahati, I was sent immediately to Agartala. Then I was given 2-3 rigs with some assistants and some other officers supporting me. And we are doing extensive groundwater exploration in Agartala. And you know, there is a famous tertiary deposit called Pipam sandstone. It's a semi-consolidated sandstone, very good sandstone, and a lot of groundwater is there in the sandstone. Pipam sandstone also form hills, they also form valleys. So whenever we get good locations to place our rig. We used to drill, and to get say 20,000, 30,000 gallon per hour is normal in Tipam sandstone. But within Tipam sandstone also there are occasional clay layers. So in many places we found multi-layered aquifer system even within the Tipam sandstone. But we never bothered that from which aquifer we should tap or which aquifer we should exploit. And aquifer-based investigation, we never bothered about that. So our intention was to drill up to 300 meter and put the strainer wherever good aquifers are there, and to see how much maximum water can come out in the well. So if it is 50,000 gallon per hour, immediately a telegram or a phone call goes to our regional director at Guwahati and to tell him, sir, we got 50,000 gallon per hour. And he was so happy. Immediately he will return a telegram to the Chief Minister of Tripura or the Minister of Water Resource of Tripura that Central Groundwater Board exploratory wells had got 50,000 gallon per hour. So there is very good groundwater. So you deploy your rigs and take out groundwater as you like. Then as the time goes on, we realize that the things are not well with the aquifer. There are multiple aquifers. Certain aquifers are getting overexploited. Certain aquifers are getting contaminated. So we must understand the time has come that we understand the aquifer-specific environment. So that is the basic reason that the National Aquifer Mapping Program comes, to develop the aquifer in a three-dimensional model and to give a recommendation how to use the groundwater in a sustainable way. It is not that you run away after saying that, okay, my aquifer map is complete, so I am going. It is not that. You have to find out which aquifer is overexploited, if the contamination is there, which aquifer is contaminated, whether it is possible to develop a groundwater-based water supply in the contaminated areas. Say in arsenic contaminated areas in Uttar Pradesh, the shallow aquifer is contaminated, but you go for community-based water development based on the deeper aquifer. That is the recommendation, and hundreds of wells are being drilled in those areas, of course with regulated pumping, controlled pumping, so that the contaminated water doesn't leak from the shallow aquifer to the deeper aquifer. So you have to give solution, you have to ensure that how the sustainability of groundwater resource will come through supply and demand side intervention. The major supply side intervention is artificial recharge. So you have to give a plan for artificial recharge. Where will be the location, which aquifer to be recharged, what will be the design, and demand side intervention. In consultation with the agronomists, with the ICAR, what will be the crop diversification? How much you can save from the smart irrigation, from irrigation efficiency? And then in the aquifer mapping, you should address the local problem and you should give local problem specific solution. This is the approach and flow for the aquifer mapping. To give you a very simple diagram, if you see my cursor, first of all, the data compilation and data gap analysis, lakhs of drilling has been done and thousands of drilling has been done by Central Groundwater Board. So whatever the data is there, you collect them. But it is not that all data will be useful for your aquifer mapping, because your intention is to go and see the aquifer specific environment. So based on the compilation, you will find out wherever there is data gap, there you will go for data acquisition. It's a big issue, and a lot of organizations are being hired for data acquisition. That is exploratory well, pumping test, geophysical survey, water quality analysis, soil filtration capacity, slug test, many. Okay, then development of lithological model and preparation of aquifer map. So a lithological model is developed and aquifer map is prepared. So you can find out, say, in the Gangetic Plain, which are the aquifer, number 1 aquifer, number 2 aquifer, this is the lateral extension, etc., etc. And then ultimately come to aquifer management plan. On the basis of that, on the basis of quality, on the basis of resource availability, on the basis of hydraulics,
how you will manage your water in a sustainable manner. So they are the 4 major steps of the aquifer mapping, and there are many evaluation steps have been created so that it is not that some officer will go and prepare some report and submit and the map is over. It is not like that. There is a national interdepartmental steering committee, very high level committee. Then at various review, it passes and ultimately goes to national level expert committee. They are not CGWB people, they are outside expert, they see it. Then state groundwater coordination committee also, they also see it. I mean to say they are checked and evaluated at various level. Then there was a huge discussion how the aquifer map will come out, because the aquifers, they don't obey the administrative boundary. Will it come out as a district? Will it come out aquifer wise? Will it come out block wise? So ultimately there was a long discussion, and we have decided that the aquifer map, its management plan, will come out as a block report ultimately. At some places it is called taluka, at some places it is called firka. So it has been done in a way. Of course, the science is there. Of course, the hydrogeological science, groundwater science is there, and the aquifers extend beyond block, beyond state, beyond district. But there is an utility aspect also. The executioner, the planners, they must be able to understand and use the report. That's why it has been decided that it will be created in a block wise. Now, this is an interesting part of, I thought that 1 minute video and photograph will tell you there are many interesting things that is coming up through our aquifer mapping. You can see this photograph, see my cursor, this is a flowing well in the desert area of Rajasthan. It's a flowing well and the sweet water is coming. Very interesting. It is coming from a paleo channel, but I'm not going to enter into that story. This is a video. I hope you can see the video. Very interesting. You see my cursor, the well is there in a hard rock area. The well is developed, being developed, but the water is gushing out from the observation well. At least you can see 15 to 20 meter distance. You can see this is the rig. See my cursor, this is the rig. The drilling is going on. The drilling is going on, and the water is gushing out from the observation wells. You see, this is the observation wells. The water is gushing out, but the drilling is going on here. Why it is happening? Because of the interconnectivity of the fractures. The well must be placed on a lineament, and you can see so well the fractures are connected that the activity is going one place and the groundwater is gushing out from another well. So this is to show you how interesting the investigation is. Of course, there are multi-dimensional investigation, but ultimately all investigation boils down into an exploratory drilling when we'll get exact picture of the aquifer. Now I will end up with my talk with an example of Maharashtra Ahmednagar district, how the aquifer maps look like, what are the outputs, and what we recommend. This is an example from Maharashtra Ahmednagar district. You know it is a dry district and the rainfall is quite less, and 2 blocks, Nagar and Nivas, I have taken about 1300 square kilometer each. And this is the location. This is Maharashtra and Ahmednagar, and typical basalt aquifer. There is a weathered zone at the top. Then there is a weathered basalt. Then there are hard basalt, massive basalt, or vesicular basalt at below, but very difficult areas. But see the interesting part. There is groundwater is very less. It is overexploited. But in spite of that, there the water intensive sugar cultivation is going on, and about 21 square kilometer in Nagar and 63 square kilometer in Nevasa block is sugar is grown, and that is irrigated from groundwater. So there is less awareness, I would say, about the scared groundwater resource, depleting groundwater resource in those areas, and they are desperate to for growing cash crop. But the farmers, they must understand that if the resource is sustainably used, it will go in a long way. It is not that you will only go cash crop and ultimately will finish off your aquifers. Next, you can see the aquifer one. So within 200 meter below ground, there are broadly two aquifers are found, aquifer 1 and aquifer 2. In aquifer 1, you can see the fracture zone, the depth of fracture zones are there. In aquifer 2, how the fracture zones at different depth they are there. So the thickness of the fracture zones in aquifer 1 varies from 0.5 to 7 meter. I told you that fractures are very thin and they are limited at different depth. So in aquifer 1, you may get 2-3 sets of fractures. If you cumulate their thickness, it will be less than 7 meter in aquifer 1 and it will be less than 5 meter in aquifer 2. Say how they are disposed and what is their cumulative thickness. They are expressed in different shades of green. And this is the declining water level, how the water level is declining in different parts of these two blocks. How the water level more red means the water level is declining very fast. And the blue level is little bit of rise in water level. This is between May 2005 and May 2014. So there are small areas where there is water level rise because of some maybe artificial recharge rainwater harvesting measure that has been taken off. But major part there is a very I would say serious decline of water level in major part of the area. Now this is the three-dimensional picture of the aquifers, how the aquifer 1 and aquifer 2 are disposed. They are the panel diagram. These are the location of the wells. You must understand this. And they are the lithological logs below. So at the top there is a aquifer 1 and at the top below there is aquifer 2 and very thin weathered zone at the top. And these are the different sections aligned in different directions. So a three-dimensional and two-dimensional picture of aquifers. And these are the, I told you this is a basalt aquifer, and the aquifer 1, this is between 10 meter and 35 meter. I mean the fractures in aquifer 1, whose cumulative thickness is 7 meter, I told you, they are distributed between 10 to 35 meter. And the fractures in aquifer 2 are distributed between 35 to 100 meter below ground. And on the left-hand side, you can see different data that we have used. 23 exploratory wells, 50 vertical electrical sounding, then hydrogeological inventory of 285 wells, and groundwater monitoring wells of 99 wells were monitored for aquifer study and water level study. And this is a three-dimensional overall picture of the area. Now these are the aquifer characteristics. This is very, very important because when you develop the aquifer management plan, they are the integral part. The aquifer 1, aquifer 2, then depth range, then static water level, then thickness of the fracture zone. I told you that if you cumulate the thickness of fracture zones, they are the 0.5 to 7 meter, but they are distributed between 5 to 35 meter below ground. Then yield 10 to 100 meter cube per day, not very high yield, 50 to 300 LPM. So 10 to 100 meter cube per day is not very high. Then sustainability up to 3 hours means if you put a pump, it will run effortlessly up to 3 hours. Then if you give you have to stop the pump, give some rest, then again you start pump, again it will work for about 3 to 4 hours. And the transmissivity is 5 to 150 meter square per day. For the deeper aquifer, transmissivity will tell you how fast the water goes through the entire thickness of the aquifer. Then specific yield divided by and storage coefficient, that the aquifer 1 is I would say unconfined to semi-confined. The specific yield is 0.02, but you see in aquifer 2, interestingly, the groundwater occurs under semi-confined to confined condition. I told you this is, the reason is that in the basalt you will get layered aquifers like in the alluvial. So in aquifer 2, the specific yield is 10 to the power minus 3 to 10 to the power minus 4. Now the suitability of drinking and irrigation, of course it is suitable. So these are the different aquifer parameters. Now to how the proposed management plan has been developed for aquifer 1 and aquifer 2. The issue is, what is the stage of groundwater development? The stage of groundwater development in that part exceeds 100% total, combining these two blocks. Now you have to bring down the stage of groundwater development to less than 70% for a sustainable use of groundwater resource. You can argue why it is 70%, why not 60%? 70% means because it has been considered that in that case the water it will come in the safe block category. So in that case your extraction will be well remain within the annual replenishable resource. Now in aquifer 1, you can see it is slightly less. The dynamic resource is 360 million cubic meter and the static resource is very, very less, 1.6 million cubic meter. So hardly any static resource is left. But in aquifer 2, the all static resource, 13.81 million cubic meter static resource is there. Now total resource is 375 million cubic meter, static and dynamic both. Our total extraction is 341 million cubic meter. Now we have to generate additional 94 million cubic meter to bring the stage of groundwater development less than 70%. So from where we will get 94 million cubic meter? We have to generate that groundwater. So then only the stage of groundwater will come low and the groundwater management will be sustainable. So there is a workout for that 31 MCM will come out of the 94 MCM that we need to save annually. Out of that 31 million cubic meter will come out from the cropping pattern change. You have to shift from the standard sugarcane to the horticulture, to jowar, to bajra. The detailed recommendation is there. 37 million cubic meter will come out from the water use efficiency measures. I mean to say, instead of flood irrigation, you go for sprinkler, you go for drip, you go for laser leveling, you go for other measures, you can save 38 million cubic meter in a year. And there must be a lot of artificial discharge and rainwater harvesting measures. So from that, you can save 25 million cubic meter per year. So that is the recommendation, and that you can see the beauty of the National Aquifer Mapping Program, that ultimately the recommendation has come that in a way by changing the cropping pattern, by taking artificial discharge measures, by going for water use efficiency, you can save 94 million cubic meter and bring your stage of groundwater development from presently more than 100% to 70%, and there will be sustainable groundwater development in that area. And this is the management plan, how from where you will manage your water that is required to make the groundwater exploitation sustainable in that area. For that you require 94 MCM, from changing cropping pattern 31, from water use efficiency 38, and from artificial discharge 25. So in many of our mindset it is there that if any water resource scarcity is there, go for artificial discharge, go for rainwater harvesting. It is not that artificial recharge is an antibiotic, it will work for all type of illness. Artificial recharge has got a limiting utility, particularly in those areas where rainfall is less, where aquifer parameters are not that good to absorb groundwater, and where the groundwater exploitation is acute. So beside artificial recharge, we go for water use efficiency, particularly targeting agriculture, because I told you that 90% of water is for agriculture, and then changing in cropping pattern, it is very, very, very important. You can see that the government of India is taking very serious view in that. That's why in the minimum support price, the last Kharif, there was a substantial increase in the minimum support price of those crops which use less water. So that is the one of the major aspects. And with this, I give you and thank you for your patient hearing. Thank you all.
Thank you, sir, for this wonderful and extremely knowledgeable presentation. There are a lot of queries.
Yes, please. I can't hear.
Dr. Sarkar, we cannot hear you. Dr. Sarkar?
Yes.
Hello?
Dr. Sarkar?
Am I audible?
Yes, we can hear you now. Yes.
Sir, thank you so much for this presentation. So we've got a lot of queries, but due to time constraint, we are going to restrict the question session right now. And most of the questions will be answered in the subsequent sessions. There will be subsequent sessions. We are looking at the questions right now. Almost majority of the questions will be taken up in the subsequent sessions, and we will also be taking up few questions later on. So I would rather insist that we continue with the new session, with the next session. Am I audible?
Yes, audible.
Okay.
I think you will continue next session, and we are available for.
Okay, so we've got a lot of questions. We are going to discuss them later on. They will be discussed in the subsequent session. I would now pass the baton to my colleague, Dr. Utsav Ghoshal, to introduce the next speaker. Thank you.
Thank you, Dr. Sarkar. Good afternoon, everyone. I welcome you all to the second session of the day one of this two-day webinar on applications of conceptual hydrogeology. Am I audible?
Yes, sir.
Okay. So, water is said to be one of the Earth's most essential resources, and rightly so. Water has become the talk of the town, and it is said that the next world war is going to be for water. So it is important for us to know how to manage our resources and to have a better future. So in this context, it is my now great pleasure to introduce Professor Pradip Kumar Sikdar to you all. He is a professor in the Department of Environment Management in Indian Institute of Social Welfare and Business Management. He is also a visiting faculty in the Department of Geology, Environmental Science and Atmospheric Science at the University of Calcutta. He is actively engaged in research and teaching of groundwater hydrology and environmental impact assessment with over 30 years of experience in project management and implementation. He is a member of the state-level Expert Appraisal Committee West Bengal for environmental clearance of development projects. Professor Sikdar has published more than 150 research papers in international and national journals, conference proceedings, books, and is the leading author of several project reports. A fellow of the West Bengal Academy of Science and Technology, he is the recipient of 22nd Diwang Mehta Business School Award 2014 for the Best Professor in Water Resource Management and Groundwater Science Excellence Award in 2015 by the International Association of Hydrogeologists, Indian chapter, in appreciation of his contributions in the field of groundwater research. So it is my great pleasure to welcome him, and I request you, sir, to deliver your lecture on water resource management, the Indian scenario, and the strategies for sustainable development. Over to you, sir.
Can you hear me?
Yes, sir.
Can you
Yes,
hear
sir.
me?
We can hear you.
Okay,
Yes, sir. We can hear you.
let me upload my presentation. Just hold on, please. Can you see my presentation now?
Yes, sir. We can see your presentation. Yes.
Okay. Okay, and you can hear me. And you
Yes.
can hear me. Okay. Okay. So thank you. Thank you, Dr. Ghoshal, for introducing me. At the outset, I'd like to thank the organizers for inviting me to this webinar, especially Dr. Utsav Ghoshal and Dr. Aditya Sarkar, and also the students of Presidency Geology Department, Presidency University. I'm going to talk about, as you all know, is water resource management, the Indian scenario and strategies for sustainable development. And, after hearing Dr. Saha, many things would overlap, but I'm going to try to avoid those. But let me see, how it goes along. And so what I'm going to do, I'm going to take you to a journey. And as we walk along this journey, I'm going to talk about this global water scenario, the Indian water scenario, the Indian water crisis. And I'm going to talk about West Bengal, and I'm going to talk about Kolkata, the city where I have lived and grown up. And then maybe some, a slide on challenges to Indian government and what could be the possible strategies for the future. And if possible, and if the time permits, I think there's a shortage of time, what we personally can do to save water. Yeah. So, if you look at the global water, you have water crisis, and the water crisis has many faces. It is a problem of quality, it is a problem of quantity. Girls in Africa walking 5 kilometers to fetch water, that's a quantity problem. In West Bengal, you have a teenage boy with the skin lesions because his village well is contaminated with arsenic. That's a quality problem. And then you have in Angola, drawing water from the local river where there is sewage dumped. So therefore, this is a problem of both quality and quantity. Now, if you look at some of the facts, we have a perception that water is an unlimited source because it falls from the sky. But we all know that water is a finite resource, and the total amount of water that is limited, and the same water keeps circulating in the land, in the ocean, in the atmosphere as the hydrological cycle. And here you can see the hydrological cycle, water falling from the atmosphere onto land surface stream ocean, then flowing through the soil into the groundwater body, and then coming into the stream network and ultimately into the ocean. And then water leaving the land surface, in the form of precipitation or transpiration. Now, I said that there is a finite quantity of water, and what is that finite quantity? That is 1.39 billion cubic kilometer of water. And out of that, only 35 million cubic kilometer, that is 2.5%, is fresh water, and out of these 2.5%, only 12.5 is usable water, and that is 4.4 million cubic kilometer. Now, these type of numbers, 1.39 billion cubic kilometer, 35 million cubic kilometer, millions and billion, we really cannot figure out. So in order to figure out these numbers, what I have done is, you can put this 1.39 billion cubic kilometer into a bucket of water and say, let's take it for 20 liter. A 20 liter is a global water. And if that is so, then only 500 milliliter of water, it is fresh water, and that is 35 million cubic kilometer, and the rest is seawater and cannot be used. And then, out of this 500 milliliter, 125 milliliter of water is again usable, and the rest 375 is in the glaciers. And out of this 125, human beings can use only 5 drops of water, which is equivalent to 4.4 million cubic kilometer, and that comes to 0.3%. So if you start from 20 liters of water, a bucket full of water, and if you take out 5 drops, the help of a dropper, that is the water that we can use. So therefore, water to us is very, very precious, and we should not misutilize this precious resource. Now, according to this report, Charting Our Water Future, the McKinsey et al. 2009, then the water demand in 2000 was 4,500 kilometer, and it's going to rise to around 6,000 kilometer cube in 2030, whereas the current availability is only 4,100 kilometer cube. So therefore, globally, there is a problem in the water sector. And if you look at, you compare with the availability to 2030, you're going to have a shortfall of 2,800 kilometer cube, and that's a substantial amount of shortage that we are going to have. Now, let's look at this. If you have an impervious cover, when you come up with urbanization, urban centers come up, and you put on an impervious cover, it affects the hydrological cycle. What happens when you have a natural groundwater surface, 50% of the water is infiltrated, 10% flows as a runoff, and 40% it moves back into the atmosphere directly as evapotranspiration. But now when you have a 75 to 100% of previous impervious surface, then what happens? Your infiltration into the groundwater body decreases substantially. Your runoff increases from 10% to 55%, and evaporation decreases. Now, what does that lead to? It leads to floods floods, and from 50% infiltration into the groundwater body, it falls to around 15%. So therefore, you have floods and you have a shortage of groundwater. So therefore, urbanization could become a big problem when you cover these natural groundwater cover and when you affect the hydrological cycle. Now, if you look at the distribution of fresh water on the earth, it's 22% of groundwater and 1% in lakes, rivers, and streams, and the rest in glaciers and ice cap. And out of this 22% of groundwater, 11% is up to 800 meters, and which we can extract. So therefore, if you mindlessly extract this 11% of groundwater, which we can extract, there would be a rapid depletion and deterioration in its quantity and quality both. And that is what is happening all over, especially in our country. So therefore, the emerging situation is water shortage. Now, remember one thing, these two numbers, 1,000 and 1,700 cubic meters per person per year, these two numbers are very, very important. If your availability is between 1,000 and 1,700 cubic meters per person, then what you are going to have a water stressed condition. And if it falls below 1,000, then you have a water scarce condition. And if it is above 1,700, you are in a good position, more or less good position. So if you look at the availability of fresh water in our, globally, then you can see in the western part over here, there is no shortage of water, but in Africa and in Asia, you see there is real shortage of water. And if you look at India, India is shown as stressed, in a stressed condition. Now, again, if you look at the global water use, 70% is used in agriculture, 21% for industrial, and 8% for domestic, and the rest 1% for other uses. Now, let's look at these. If you look at this is in various countries the water usage, and if you pick up India and USA, see India, about 90%, more than 90% of water is used in the agricultural sector, whereas in USA, it is 65% of water is used in industrial sector and only 27% in agricultural sector. In India, around so therefore, if you want to develop management models, our management models, we should not pick up management models from the Western world. It should be our own management model. We should look into our agricultural sector more and try to save water there. That is very, very important. And apart from, artificial recharge, rainwater harvesting, maybe industrially, increasing the productivity, those are the other things. And safe water, for domestic use, that could come in the later stage. But substantially, we need to save water in our agricultural sector. So therefore, we should not copy, other models. We should develop our own models of water resource management. Now, if you look at again the evolution of global water use, if you give more water to people, water will be wasted. More water will be wasted, both all in the agricultural sector. Look at the domestic sector. The more water you give in the domestic sector, the more wastage we are going to do. Similarly, in industrial sector, and if we construct more dams and reservoirs, there would be more of evaporation, loss of water through evaporation. So therefore, we need to how much water, what should be the supply of water, that is very, very important. We need to cut down our supply also. If we cut down our supply, then possibly our wastage would be, reduced, especially in the domestic sector. You can see it's a huge gap between withdrawal and consumption. Now, if you look at the sectorial water use, developing countries, they use more water for agriculture, whereas the developed nations, they use more water for developed nations use more water for industrial and domestic sector. And if you look at Asia, globally, Asia is a big problem. If you look at people and water, it's uneven. If you look at America, North, Central America, South America, you have less people and you have more water. But you come down to Asia, you come down to Africa, you have more people and you have less water. And if you look at Asia, Asia has 60% of world population and 36% of world's water. So therefore, it's really uneven. So therefore, Asia is a region with challenges: 60% of world population, 2/3 global population growth, increase in urban population by 60% by 2025. So therefore, you have serious water challenges to sustain population and economic growth. You need water for basic needs. You need water for the growing cities. You need water for food. You have a growing population, so you need more food. And so therefore, you need also more energy. And all these would be affected by climate change. And so therefore, the problem would be even more. And if again look at the cities, cities are growing and cities are becoming more thirsty as more and more cities are growing and small cities are developing into large cities. And even in the coastal areas, you have challenges because more than 1/3 global population lives in less than 1 kilometer from the coast. More than 1 billion in coastal centers and 50 million moving to coast every day. So therefore, it is a zone which is under severe pressure. So this is another area where students can take up research in the coastal challenges or in the urban areas. Now, if you come down to the Indian scenario, now India has plenty of rainfall, 4,500 kilometer cube of rainfall. And of this, 250 kilometer gets stored in dams, 440 kilometer flows into the river and is available as surface water, and 432 kilometer gets stored in aquifers, and the rest around 3,378 kilometer of water flows into the seas and ocean. So therefore, you have somewhere around 1,122 kilometer cube of water. Now, if you look at the water used by sectors, agriculture, 90% of water is used in the agriculture sector. And if you compare that with the global, it's 70%. And then if you look at the industrial sectors, we use only 2% in industrial water, whereas the world average is 22%. Domestically, and we are at par with the global average. So therefore, the thing that comes out is how efficiently do we use our water. So let's see that. In the agricultural sector, 688 billion meter cube of water is being used. Now, if you look at the major, the crops, that is wheat, rice, and sugar, and the water that, the water footprint for wheat, rice, and sugar for India, and you compare that with the global water footprint, you can see we are much, much ahead. Our water footprint in wheat, rice, and sugarcane is, wheat and rice is pretty high. Sugarcane, we are a bit less than the global average. But look at the virtual water use. If you look at the virtual water use, and if you compare with some developed US and China, you can see virtual water is used tremendously in our country. So therefore, when you are exporting, and if you're exporting rice, if you're exporting wheat, or you're exporting sugarcane, what you are actually doing, you are exporting water. And that is a big problem. So therefore, in agricultural sector, it is overuse and it is inefficiency. So therefore, what possibly we need to, or we actually need, is to adopt modern irrigation methods. Now this is, water is consumed. This is virtual water type of thing. 1 cup of tea, 35 liters. 1 cup of coffee, 140. 1 egg, 135. 1 glass of milk is 1,000 liters. This is strange but true that when we drink a cup of tea, it's not the water, the cup that is full, or the water that is in a cup, but is actually 35 liters that we are consuming. So when you are exporting Darjeeling tea, you are actually, for 1 cup of tea, you are exporting around something slightly less than 35 liters of water. So now if you come to the industrial sector, what we are using is 15 billion meter cube of water. But look at this number over here, 7.5. Now this is the industrial water productivity. This is in US dollar per cubic meter. And if you compare that with the other countries, then you can see our productivity is so very low. So therefore, that is the biggest problem in our industrial sector, is that our water productivity is very, very low, and we need to buck up in that area. Now again, the domestic sector, it is again 56 billion meter cube of water that we are using, but then the problem is we have a distribution system is a problem in the urban areas. You have slums, and then you have also high rises. So there is an inequitable distribution within the urban areas and urban population. And then also you have an inequitable supply of water between urban and rural Indian. So therefore, again, you have a bit of problem. So, but the problem here is a supply side problem. Now, let's look at the wastewater generation. We generate like 18 billion meter cube of water. And out of that, the industrial wastewater is 13.8 billion meter cube, and domestic is 4.2 billion meter cube of water. Now, the problem is that treatment of this is a big problem, it's a big issue. Only 30% and 70% of sewage from Tier 1 and Tier 2 cities is treated. The rest is discharged untreated into the rivers and fields. So therefore, if you discharge this untreated water in a sewage wastewater, then you are contaminating not only your surface water, you are contaminating your soil, and even you're contaminating your groundwater. So therefore, we need to think about, when we think about water management in our country, we need to think about wastewater recycle and reuse. And that could be the new water resource and help to reduce the water stress that we are facing, and we are going to face more in the future. Now, if you look at the water crisis, there was a report way back in 1996 that the water requirement in India will be 1050 in 2025. Now, if you look at this number, 1050 cubic kilometer, you can see it's fine. And if you compare that with 4500 kilometer cube of water, that the rainfall that we have, we are in a good position. But then the problem is, again, we know that our utilizable resource is somewhere around this 1120 to 1150. So I picked up this 1150 kilometer cube. And if you compare that, whatever water you're going to use in 2025, that is now 1050 cubic kilometer. So that means you're using 91% of the total available water. So you have only 9% of your water available water left every year. And that is the biggest problem. You cannot use 91%. So therefore, at least you're going to overuse your water. And apart from that, apart from this 91%, the problem in India is that the water is not uniformly distributed. If you just look at the Brahmaputra basin, you see its country's area 6%, population 3%, and water resource is 334 cubic kilometer. That's somewhere around 29% of water. So you have 29% of water in Brahmaputra basin, and your population is 3%, and country's area 6%. So that is an inequitable distribution of water in our country. And if you compare that with some of the southern and western region, the availability is much less than the national average, which is somewhere around this 1,550 meter cube per capita per year. So therefore, if you look at the river basins, water and stress, you can see Dr. Saha also stressed on that. On the western part, you have water scarcity, and even in the southern part, you have water scarcity, and in the Brahmaputra, you have some, you get good quantity of water in Mahanadi, Godavari, and some of these river basins. And these are some, again, 200 million Indians do not have access to safe water. 90% of country's water resources are polluted with untreated industrial and domestic waste. River Ganga is no longer usable. Out of 80 districts make up Yamuna, 62 districts experience water stress due to acute pollution. 3,000 crore litre of sewage generated, 200 crore litre treated. CPCB says around 50% don't have this wastewater treatment facilities, but things are improving now, I can say. There's a Ulhas River where you get even in the in the riverbed you get these heavy metal, lead, zinc, chromium, copper, and cadmium. In Kerala, most of the rivers are polluted with heavy metals. Now, if you look at the Ganga Delta, around the Sagar Island, there is the presence of phenol, which indicates that there is industrial pollution in this water. You have such metals like copper, lead, nickel, cadmium, chromium, manganese, and iron. And fecal coliform number is very, very high in lakhs, mpn per 100 ml of water. It's in lakhs. So that's, fecal coliform is, it's a major problem in the water in West Bengal, or especially say in the down, even in the Sagar Island and in the Sundarban areas also. Then if you look at these, the estuarine water, Sagar Island, Sagar Island is famous because we take the holy dip there, and it fails to meet the stipulated standards for class A, B, C, and E. And water can be classified only under class D. So therefore, which is water for fish culture and wildlife propagation. So therefore, this water is not even fit for bathing, but then lakhs of people bathe in this water during the annual Mela in winter. Now, if you look at the India's groundwater quality problem, you can see in all the states you have some problem or the other. And if you zoom down to West Bengal, here you can see there are 6 problems. The first one is salinity, then you have fluoride problem, you have iron problem, you have arsenic problem, you have nitrate problem, you have chloride problem. And to me, you can add one more, manganese is an upcoming problem in West Bengal also, and we need to look into that. Now, if you look at the geogenic groundwater pollution, arsenic is 86 districts in 10 states, fluoride 276 districts in 20 states, salinity 9 states plus 4 union territories, nitrate 387 districts, 21 states, iron 297 districts, 24 states plus 1 union territory, and heavy metals in 113 districts of 15 states. And when we talk about it's lead, cadmium, and chromium. And, if you look at the arsenic crisis, that's a major crisis in West Bengal. It's not only in West Bengal, even in Bihar, and all the red areas that I can see over here, these are this covers around 500,000 square kilometer with a population of around 500 million people who are at risk. And the people drinking this arsenic-rich water, they develop melanosis or keratosis or even advanced arsenicosis. And even some people are dying because of cancer because of drinking excess arsenic water. Then again, fluoride is distributed in all over the country, and you can see in the western and in the southern it's profusely distributed. And you can have skeletal fluorosis or dental fluorosis by drinking this fluoride-rich water. Now, Hindustan Times, May 11, 2019, they came out with this, that 14.7 million Indians drink arsenic-contaminated water. But the ministry's data reveals that 14.7 million people are at risk due to arsenic-contaminated drinking water across 16,889 areas. And the Economic Times in December 11, 2017, they said that 100 million people drink contaminated water in India. And, our government has taken steps to provide safe drinking water to about 28,000 arsenic and fluoride-affected habitations over a span of 4 years. And in India, about 38 million people are affected by various waterborne diseases. Now, World Bank says 21% of all communicable diseases in India are waterborne. We tend to lose about $8.3 billion or 336 billion rupees per year for waterborne illness. 1.5 million Indian children die every year. And India also loses more than 200 million work days because of these diseases. Now, India has, this is important, India has 4% of world's annual renewable fresh water, whereas it has only about 2.5% of world's total land area. Therefore, people say that if you have 2.5% of world's land area and you have 4% of world's annual renewable fresh water, then you should be water sufficient. But, there is a catch. 90% of the total water requirement is for agricultural purpose, and 12.5% of world's arable land area is in India. So you have 12.5% of arable area, and you have only 4% of renewable fresh water. Apart from that, India has to manage more than 17% of world's human population. And 15% of world's animal population. So therefore, if you have to water and you have 12.5% of water, that means we are agriculturally rich land. So therefore, we are actually with only 4% of world's annual renewable fresh water. India is actually water deficient. And a major part of India will experience droughts and famines much before 2025, even if we have normal monsoons every year. And if you look at the annual per capita availability of renewable fresh water, in 1951, it was more than 5,000 meter cube in its per capita water availability. In 2011, it dropped to 1545. So from a water sufficient condition in 2011, we have dropped into a water stressed condition. And because it's less than 1700, and it is projected that it would be, the condition is going to worsen. It would be around 1341 meter cube, and 255 is 1140. So we are going to move more towards the water scarce condition. So therefore, India possibly would be water stressed, and it is water stressed even before 2025. And so therefore, what we need to use is our own wisdom now, and to manage our water resources. So therefore, this could be our reality, drinking water 100 per liter, and even petrol, it's around 82, 83 liter per liter now moving, but it could be, drinking water is around 20, 22 liter per liter, but, the cost is going to increase fast. Now, let's zoom down to West Bengal. Now, if you look at West Bengal, the total area of West Bengal is 88,752. Leaving you have 23 districts, 341 blocks. But the major problem with West Bengal, if you look at the population density, if you compare that with India, India has a population density of around 322% per square kilometer, whereas in West Bengal it is 1028. So that's the biggest problem, or the biggest challenge in water resource. Now, in the West Bengal has three major basins. You have the Brahmaputra basin, you have the Ganga basin, and you have the Subarnarekha basin. Now, this is very, very important. West Bengal is a hydrologically subsidized state because it is located at the tail end of the Ganga basin, and it is hydrologically subsidized state, and the state receives more than 588 billion cubic kilometer of transboundary water, and because of this transboundary water, we have plenty of water. But the supply of this water is so skewed that West Bengal bears the brunt of flood during monsoon and faces water shortage during the lean months. Now let's look at the water resources of West Bengal. Average precipitation is somewhere around 1800 millimeter. The availability of water is around 159.27 billion cubic meter. And out of that, surface water, the water that we can use is 77.06, groundwater 29.25, and the natural discharge from the groundwater is 2.67 billion cubic meter. And so therefore the internal resource, water resource that we have is 103.64 billion cubic meter. And the total water demand is 150 billion cubic meter. So therefore there is a shortage of water, with the own water, the water that we have from the precipitation. But West Bengal is surviving because of this transboundary water. Now, if you look at the per capita availability of water, it has again, declined sharply. 1951, it was more than 4,000 meter cube per year, but in 2011, it was 1158 meter cube per year. So therefore, there has been a sharp decline. It's below the 1700 mark. So West Bengal is a water stress state. And if you look at 4 districts, Nadia, Howrah, North 24 Parganas, and Kolkata, per capita availability is even less than 500 meter cube, and hence these districts are absolute scarcity area. So, and if you look at the total number of blocks, you have 341. And if you look at the stage of development, West Bengal stage of development, that is the existing groundwater trough by the net annual groundwater availability, is 44.60, whereas the stage of development is somewhere around the 60% mark for India. And if you categorize the block, this is according to 2017-18 yearbook, number of safe blocks out of the number of blocks assessed is 269, safe blocks is 191, semi-critical blocks are 76, and critical blocks is 1. And if you look at, these are the locations where you're going to find the semi-critical or the critical blocks in West Bengal. And then apart from that, you have the quality problems, arsenic, if you consider 10 microgram per liter, 104 blocks in 11 districts. And if you consider 50 microgram per liter, then it is 83 blocks in 8 districts. But now we are, we are going along with 10 microgram per liter. Fluoride, 43 blocks in 7 districts. Salinity, 53 blocks in 4 districts. And nitrate problem, you have 7 blocks in 2 districts. Now you can see the arsenic contaminated areas in West Bengal. These are the fluoride contaminated areas in West Bengal. Down south you have the salinity affected areas, and then again in the west you have the nitrate affected areas. Nitrate is more than 45 milligram per liter. And so if you combine all this, you can see you have problems all over West Bengal. In the north you have some pockets where you have arsenic, then you have fluoride. Around the eastern margin you have arsenic, on the west you have fluoride and nitrate, and down south you have salinity. So there is a quality issue in West Bengal apart from the quantity issue. So even if you look at eastern state, if you have plenty of water, it's 44% the stage of development, the stage of development is around 60% in India. So we have, good, we have water that can be used more for agricultural, industrial, yes, but that is from the quantity point of view. But from quality point of view, you have to have, there is a big question mark whether we should need to, combine. So because if you have arsenic in water and you are using that arsenic water for your agricultural purpose and you go on increasing more, then that would go into the food chain. And even from the through this food, through this rice, this arsenic contamination would spread even outside the areas where you have arsenic contamination. Again, out of 269, if you take 0.5 milligram per liter of water, 66 blocks are arsenic contaminated, and out of that, 20 blocks are semi-critical and 46 blocks are safe. So therefore, if you 66 blocks, is semi-critical, if these are safe blocks, 46 blocks are safe, but the question arises whether it is actually safe or not. Then again, from out of the assessed blocks of 42 blocks of fluoride affected, 42 blocks have been declared as safe. But remember one thing: these are from quantity point of view, but from quality point of view, this I think this cannot be said to be safe. Okay, now if you look at the district wise, you have the stage of development is pretty high in some of the districts, as high as 87.43, and then there are some districts where you can see that there are the stage of development is pretty low, even below 30% or even below 40%. But apart from but even if it is, if the stage of development is low, but still you have other problems. Other problems mean you have the quality issues, and then there could be a problem of whether this arsenic. You do have bouldery aquifers where drilling of wells becomes pretty difficult. And again, you could have laterites, where drilling could be difficult, and the amount of water available could be as low. So therefore, each of these districts, they have their own problems, and so therefore you have to look into this local level and see whether, even if you have 44% of stage of development, but again, you need to see this low development, where the districts where there is low development of groundwater, but whether you can really extract groundwater or not. Now, coming to the groundwater of Kolkata, if Kolkata, if you look at this is Kolkata, and then you look at on the eastern part of Kolkata, you have the East Calcutta wetlands. You have, this is the Dhapa solid waste dumping ground, where all the city wastes are being dumped over here. Then you have another city, it's called the Salt Lake City or the Bidhannagar. Then you have the upcoming new city, which is called the Rajarhat. And then you have this agricultural land, and then outside the wetland area, you have the Calcutta leather complex. So therefore, this is a real area where, it's very, very interesting. Kolkata's groundwater is very, very interesting because, you have huge pumping of water. You have, this Dhapa solid waste dumping ground where you could have pollutants coming into the groundwater from the Dhapa solid waste dumping ground, from the wetland areas, from the agricultural land, because agricultural land is all over. You have huge quantity of waste coming out in a solid waste, and chromium which is coming out. So that could, and because of this huge thing of water in Kolkata area, there is always a flow of water from the east to the west towards Kolkata city. I'm going to come to that. Now, if you look at the subsurface geology, which is based on 109 borehole logs, you can see that, in the first upper 15 meters, you're going to get a gray clay, followed by, this is gray clay is Holocene in age, and then you're going to get a brown clay below this 15-meter depth, and this is your Pleistocene brown clay. And below the Pleistocene brown clay, you're going to get yellow or brown sand, and therefore gray. And then below that, you're going to gray sand. And so therefore, if you look at these areas where you have prolific sand, these are the areas where you have majority of the wells, and these wells are continuously being pumped. You have private wells, you have government wells, you have hand pumps, all pumping out water throughout the city. And then around the depth of 150 meters, the clay slightly increases, but then again, if you go below 200 and around more than 220 meters, the sand again increases. And so therefore, and below 300 meters, you have a grey clay, which actually continues up to a depth of around 600 meters. So that's a very, very thick clay. So therefore, this entire area, right from say around 90 meters or 70 meters downwards, up till about 250 meters, you have the major aquifer of Kolkata. And if you look at the sedimentary sequence, this is, if you look at this, over here, this is the section. You can see the upper clay, which we call around 40 meters in average thickness of this upper clay aquifer. But this upper clay aquifer, the thickness varies sharply. In some places, if you look at this over here, 39 borehole number, you can see you do not get this clay. So therefore, there are areas in Kolkata where you have around 60 meters of clay thickness, but in some areas where you do not have any of the clay thickness in the upper part, and you have sand starting right from the surface. So therefore, in these areas, these are very small pocket areas. I'm going to show you that later on, that these are the areas where the groundwater is in an unconfined condition, but in majority of Kolkata's area, you have confined condition, and you have unconfined condition where you have these paleo channels actually. Now this is basically the three-dimensional see, where you can see you have a clay, top clay, and then you have a brown, a gray clay at the top, and then a brown clay, then a brown clay, and then the brown sand followed by this gray sand. Okay, so so this is the last glacial. This brown clay is called the last glacial maximum paleosol. And I'm not going to talk about this paleosol. Maybe in some other lecture I'm going to talk about. But these paleosol is very, very important from arsenic point of view. Presence or absence of this paleosol is very, very important from arsenic point for concentration of arsenic in groundwater, and also the presence of brown sand. Also, it determines how much arsenic you're going to get in water. If it's brown sand, you're going to get an arsenic-free water. If it's gray sand, you're going to get arsenic-rich water. Okay, and look at this. This is, this is a river which is flowing. This is known as the Adi Ganga, which is now known as the Tolly's Nala. And if you look, this is at the top over here. This is the Hooghly River, and this is basically, and this is the, this Tolly's Nala, which was previously in long past, and it was the actual, course of the river Ganga, and so we call it the Adi Ganga, or now we call it the Tolly's Nala, which has been silted up. Now let's look at Kolkata's water supply. Now, Kolkata's, the actual water supply, the municipal corporation, they supply 2027.50 million liters per day of water. Now, if you look at, and in Kolkata, you have a resident population of around 4.5 million, and we have a pretty large floating population who comes into the city and moves out, and that's around 6 million. And according to the government average floating population 40 liters per day and resident 150. So then 915 million liters of water is required for the drinking and domestic purpose. And for industrial, and we also supply to our neighboring municipality, that's around 2030 million liters per day. So therefore, if you look at total requirement is actually 1245 million liters per day, whereas the municipality is actually supplying 2027.50 MLD. So therefore, where is this water going? So around 782.5 million liters of water per day is being wasted, and this wastage of water is around 38.6%. And so therefore, in Kolkata, this is a big problem. This wastage of water is a big, big problem in Kolkata, and we need to cut down this wastage of water if we have to have a sustainable water management for this city. And if you look at the groundwater development pattern, in the mid-50s, it was 55 million liters per day. And then presently it is somewhere around 305 million liters per day. So therefore, a huge quantity of groundwater abstraction has taken place over this last 60, 70 years. And let's look at what are the hydrogeological consequences of over-extraction of groundwater. Now, if we assume that there was no water there was no groundwater abstraction in the city and its neighboring area, then this would have been the distribution of head under the natural flow condition without any pumping. And this is model derived, okay? And if you look at the groundwater flow, you can look at the arrow, it's from the northwest to the southeast, and this is the natural groundwater flow system, or which I call it the open groundwater flow system. Now, because of this unplanned groundwater extraction in the city, this is how, over the years, the groundwater flow pattern has changed. If you look at mid-50s, it was the open groundwater flow from north to south. But then in the pre-monsoon of 85, you can see that the groundwater flow pattern has completely changed. And now you have groundwater, you have a central trough, groundwater trough, which has developed in the heart of the city, in the central or the east central part of the city. And you can see that the flow pattern has changed from an open flow system to a closed flow system, and it's radially inwards because of this development of this groundwater trough. And then if you look at 1985 post-monsoon period, the trough continues, but only what the difference is that there is a slight rise in the water level by around 1.5 meters. But then if you look at 1993, again, what happened is this trough has widened. It has widened in the north to the south, to the east, and to the west. This is widening. So therefore, this actually indicates, and again, if you look at the pre-monsoon period under more or less under current current pumping, then you can see you have this groundwater trough in the central part of the city. And so therefore, this actually indicates that both in the pre-monsoon and the post-monsoon, the water level is continuously falling. And so therefore, the groundwater of the Kolkata city is highly stressed. Okay, so and you need to develop some groundwater management plan in order to, so that the stress could be reduced. And now, if you look at this groundwater trough, I picked up the 1985 trough from the figure. That's my own figure, and I drew it over here along with my student, my PhD student. And what we found that if you pick up the minus 10 meter contour, and that indicates the groundwater trough, the contour for the groundwater trough, and which is represented by minus 10 meter, it's increasing. Now the middle one, this over here, this is your 1985 trough. This, the other one, the light blue over here, this is your 1994. The pink one is your 203. This is minus 10 meter contour. So this, you can see how the area is increasing. And it's increasing more towards the southwest and to the west. And if you look at this, this color over here, the blue, this color, this is the 2016 minus. So this is the minus 10 meter contour line for 2016, and you can see that the trough is actually increasing, or in other words, the groundwater in the city is falling at a very rapid pace. Now, if you look at the built-up areas in 1985, 1994, 2003, and 2016, you can see that the built-up area is also increasing. And if you look at this over here, if you look at this is the area of the groundwater trough. It's a plot of area of the groundwater trough, and in the built-up area, you can see the exponential growth of this groundwater trough along with this built-up area. So therefore, built-up area, urbanization has been the major cause of this falling groundwater level. And then now let's look at the recharge areas of groundwater of the city, and what you can see that pre-pumping the water used to come from far off in the north and also from the east. But with the current pumping, the recharge area has come very close, and in the pre-pumping stage, it was all coming from arsenic-free area. But some water from now is flowing from the arsenic-polluted areas. Now, this is another map, way back in 1996, I prepared it. It is the estimated land subsidence in Kolkata. But visible evidences generally have not been, except for one which happened very recently in Bowbazar area, where because of this tunneling for metro railway, there was this land subsidence in Bowbazar area. But in general, the surface expression is cryptic because of the time lag between settlement of thick, low permeable aquitard, made up of clay and silty clay, and its surface expression. So because, it's with very low permeability and a thick clay, clay to silty clay body around 40 meters on average, the surface expression is very, very cryptic in city. But this is, the area where this was affected by land subsidence because of this, tunneling for this metro railway, below the city. And this is, you can see on the picture on the left, how the buildings came crashing down, and cracks were formed in the building. And so therefore there was a lot hue and cry on this. And then again, Kolkata's groundwater is also affected by wastewater. If you have plots, this is chloride by bromide versus chloride plot, and if you have your plots around this area, that means your water has been contaminated with wastewater. If it is on this blue line over here, so that means it is your water has been there's a seawater mixing with the fresh water, and if it's below this line, then there is a case of organic degradation. And in case of organic degradation, bromide is concentrates more than chloride, and so therefore your chloride bromide ratio drops, and your seawater mixing line is somewhere around this the chloride bromide value ratio is 288. So if you have somewhere around more than 300, so therefore it is definite that your water is contaminated with wastewater. Now if you And why? Because our sewage water, if you look at our water, the sewage, because we take a lot of sodium chloride, so therefore our chloride bromide ratio, and we excrete more of this chloride, so therefore the sodium chloride, chloride by bromide ratio increases in sewage water. And now if you look at, this was around 280 wells, both hand pumped wells and municipal and private motor pumped wells that we collected samples and we analyzed. The hand pump wells had a medium depth of 91 meters, whereas the municipal and private pumped well, they had a median depth of 121 meters. And if you plot that in that chloride bromide versus chloride diagram, and what we find that there are about 14% of municipal wells and 33% of public wells that have chloride bromide above the marine mixing line, and so are contaminated with anthropogenic chloride from black water. And this chloride, this anthropogenic chloride, has penetrated to around 130 meter depth. So you can see this is the sample where the chloride bromide ratio is more than 300, and so therefore, and that is a distinct evidence that wastewater has gone down even up to a depth more than 100 meters. And you can see at 100 meters the chloride bromide mass ratio is pretty high. And if you plot these high chloride bromide ratio water, and you find that these water plots mostly close to that Adi Ganga or the Tali's Nala, and this is because the river incision along the Tali's Nala provides a conduit from surface to the underlying late Pleistocene aquifer. And as I mentioned earlier, that here you have an unconfined system along this floodplain of the Adi Ganga river. And this is the Tali's Nala, which are the Adi Ganga, and you can see the makeshift latrines over here. So, and these continuously it's being used, and so therefore you have sewage contamination, and you have pumping all around this nala. Huge pumping is going on, and so therefore you have a vertical flow, and the water is flowing, and because you have an unconfined system, the water is flowing deep, and it has gone to somewhere around this 130 meter. You get evidences of waste water. So therefore, this is another thing that needs to be looked into, and we need to, this Adi Ganga or the Tolis Nala should not be used in such a manner that is being used at the present moment. It should be cleaned, and water should flow. This is a tidal Nala. When there's high tide in the Ganga, the water comes into the Hooghly, and when the tide goes out. But then again, because, I don't know, because of our foolishness or whatever, I don't know, we built our metro railway on this Talis Nala. We have big pillars right along the coast of this Talis Nala, which is actually, so what is happening is, the flow velocity of water is dropping because it's hitting this pillar, and so therefore, you have a huge rate of sedimentation when the tide comes in and when the tide goes out, and so therefore the riverbeds is rising. So you have floods, more and more floods in this part of the city during the rainy season, and because of this, makeshift latrines, you have bazaars, throwing their waste, and all sorts of sewage is coming into this. You have sewage outlets into this Tolis Nala, and so therefore, the entire aquifer system is being contaminated with wastewater. So we need to look into this. And then, there are some papers which says that Kolkata's aquifer, you have plenty of arsenic. You can see, in most of the areas, it is more than 10 microgram per liter or 10 ppb. But then, the sampling that we did, along with Professor MacArthur, the analysis was done at the university, in his university. And what we came across is that only 2 samples out of this 280 samples all across the city, you can see the small squares, over here, these are the sampling locations. Only 2 samples were more than 50 microgram per liter, and 11 samples were in between 10 and 50 microgram per liter. 7 samples were between 5 and 10. So therefore, if you look, 11 plus 2, 13 samples were actually more than 10 microgram per liter, and the rest of the sample was around 267 samples was below this 10 microgram per liter. Now, and if we plot this on the map, what we found that this high concentration arsenic groundwater is located all around this, along this Tolis Nala or on the floodplain of the Adi Ganga. And why? And this could be traceable to an industry which used to produce Paris green, and which is it was known as the Acetochemical Private Limited, which used to produce Paris green, and it is rodenticides which used to use arsenic, and the waste for more than 30-40 years, the waste was dumped within this factory premises. And it was there, now you can see this triangle. This triangle was actually, this triangle is the ACPL site, which was absolutely bang onto the floodplain of, so therefore the groundwater was unconfined. And so, with years, with heavy pumping on all sides, and also even because of heavy rainfall, there was continuous infiltration or leaching of these pollutants or arsenic into the groundwater body, and then it moved deeper into the aquifer system. And what we get is, these are the areas, those who are acquainted with Kolkata, this Behala, Taliganj, Rajbihari, and Alipur, these are the areas where groundwater is actually affected with arsenic, but the rest of the city, there is no groundwater. So that's a good news, I think, and I believe there is no groundwater arsenic. And if you look at the schematic section, now this is the last glacial maximum paleosol, which is somewhere around, below this 15 meters or somewhere on this 20 meters depth. And here you had this, originally you had a Pleistocene channel, which we call the Adi Ganga. Later that was silted up, and then a canal was constructed, which we now call the Tolis Nala. And this, unknowingly, this factory, which used to produce Paris green, was located on this floodplain, and the aquifer there, it did not have, because there was a river system, there was no, this paleosol was not developed, so therefore there was no barrier for this arsenic. So the arsenic slowly moved down because of this pumping all over this place into the aquifer. Now, let's look at the challenges, So if you look at the challenges, what the India government is facing, now if you come back to the India from nationalistic point of view, the challenge from agricultural sector is to meet the increased demand from existing resources. So we have to change our cropping pattern. We have to go in for this drip irrigation. These are the things that are must. So because 90% of our water is used in agricultural sector. Now, in our industrial sector, we need to recycle and recycle our effluent. We have to be very, very careful about the sludge disposal. That's the challenges over there. We need to increase our water productivity. Water productivity is abysmally low in the industrial sector, 7.5. And then, so therefore, what we need to do, we need to adopt modern technology. So that's again a big challenge for the industrial sector. And for the domestic sector, the challenges are we need to find out new sources of water supply, find out new aquifers, deeper aquifers, where the groundwater is, relatively it's not being used, and is also quality-wise, it's also good. And I think Dr. Saha also mentioned that there are many aquifers, the second aquifer, which is being pretty high use. You can go into the third aquifer, even if fourth aquifer, you can go. But remember, really very sure that these aquifers, it's really an. Hello. Hello.
Sir, please continue. We can hear you.
Sir, yes, we can hear you, sir.
Okay, something happened on this side.
But we can't see your PPT. We can't see your PPT.
Yeah. You can't see our PPT. Okay.
Yes, okay. Now we can see it. Now we can see it.
Now you can see it? Now you can see it?
No, sir.
It just gone. Yes. Right now we can see it.
Okay, fine. Okay. So therefore, we have looked into these challenges for the future, the agricultural sector, the industrial sector, and the domestic sector. Now let's come to what could be the strategies for the future. Now, let's look at the strategies, for any sustainable water management strategy, what I believe, generally we look into the supply management and we look into the demand management. Dr. Saha looked into that, talked about supply management and demand management. But these are the two main pillars. But apart from these two main pillars of supply management and demand management in a sustainable water management strategy, you need to talk about population management, at least for Indian perspective. That's also very, very important. And there is even a fourth pillar which I'm not going to talk over here, and that's the gender management. It's another important from sustainable water management strategy, and I'm not going to talk. I'm going to talk about these three pillars. If you look at the supply management, you need to get rid of these big dams, big reservoirs. You need to go in for the soft engineering techniques of construction of check dams and impoundments of water. You need to go in for a massive scale rainwater harvesting and artificial recharging. Then you need to have a sustainable exploitation of groundwater. You need to reprocess your wastewater, recycle your wastewater. Then, you could also go in for desalinization of brackish water. And then another important thing to increase your supply, you could reallocate water from one user sector to another user sector. Now, demand management, you need to cut down on the demand management. You need to have special incentives and water saving mechanism. You need to increase your water productivity. You need to change your cropping pattern. You need to adopt appropriate pricing policy. At least in this part of the country or in West Bengal, water is a free commodity. And so if you have anything free, you waste more. So you need to think about that. And an important thing is, the people in the slum, the poor people in this urban city, they are subsidizing water for the urban rich people, and that should not be there. Okay, otherwise your demand is going to go on increasing for the urban people, and therefore you cannot have a control. Then popularizing conjunctive irrigation is another bold step. Now, another important thing, as I said, is the third pillar is the population management. If you look at our population, now our population is presently more than 130 crores, and this is going to grow at a rate of 1.2% per year and will stabilize somewhere around the end of this century at 180 crore. Now, we can only supply water to 150 crore of people. But this 150 crore, supplying water to 150 crore comes with three riders. Number one, you need to stop wastage of water. And you see, even in a city like Kolkata, you are wasting around 40% of water. You have to stop wastages, you have to stop pollution of your water courses. And another important thing, which, people we can try to do. But then the third one is very, very, we do not have a control that monsoon would never fail in the future. So if you have these three riders, you cannot waste water, you cannot pollute water, monsoon would never fail. If that is so, then you can sustain a population of 150 crore. Otherwise, you cannot sustain the people that we have. It's now somewhere 135 crores possibly. So therefore, this population management should also be a big challenge for sustainable water management. So therefore, I believe the next challenge before India, and possibly the only way to save ourselves from the impending water famine, is to check the rapid population growth so that the population does not go beyond, I put a question mark on the crore. So therefore, now coming down, the last part of my presentation, what we can do. Government can do many things, but we individually, we can also do many things. We can only use the amount we actually need to not waste water. All of us need to form a group of water conscious people around us. We need to encourage our family to keep looking for new ways to conserve water. We need to be sure that our home is leak free. You do not have a leaking tap. You do not have a leaking closet. Do not leave the tap running. We tend to do that many times. We tend to leave the tap running. But, we shout at when the light or the fans are on, because at the end of the month we have to pay a heavy price for that. But for water, we do not have to pay anything. So therefore, why not leave the tap running? And on the roadside, if you put in a tap, then what happens? Somebody steals it and puts it at home, and then the water continuously leaks. So you should not have a leaking toilet tank. You should avoid flushing the toilet unnecessarily. When washing the car, use water from a bucket and not from a hose pipe. Do not throw away water that has been used for washing vegetable. You can use it if you have something some small garden on your roof. You can use that water to water those plants, and you can store water in a variety of ways. You need to look at things or do something simple to save water. Even we should not worry if it is minimal, because when we act together, the huge population, every drop is going to count, and we ourselves can make a difference, and especially on this wastage of water. So, what I personally believe is water is a right. It's not a commodity. It's for our sons, for our daughters, for the earth, and for the people. And we should stop wasting water, and we should find means and ways of wasting water, and to how to cut down the supply of water, or increase the supply of water, I would say, and cut down our demand, and also manage the population for a sustainable water resource management. Thank you very much for your patient hearing.
Thank you so much, Professor Sikdar, for your wonderful and informative presentation as usual. Before I start the question and answer session, I would like to hand it over to Dr. Sarkar again for some important announcement. Dr. Sarkar, over to you.
Thank you, Dr. Ghoshal. So first of all, I would like to inform everyone that due to time constraint and due to his busy schedule, the previous speaker, Dr. Dipankar Saha, had to leave early. However, he has graciously agreed to answer all your questions through email. So we are compiling the questions you have sent us regarding his session, and he will be answering them shortly. Regarding the attendance to these sessions, there is a protocol that has been set. Those people who have entered or logged into the Microsoft team with their names need not to worry about the attendance. Those who have logged in as unknown people, or they have not logged through their name, have to give their name on the chat box. Those who have logged through YouTube also have to give their names and details in the chat box section. This is important so that we can, count your attendance for the e-certificates. Thank you. I will now hand it back to Dr. Ghoshal for the subsequent session.
Thank you, Dr. Sarkar. We can start the question answer sessions. I have a few questions. So we have a few questions for Professor Sikdar. Sir, the first question came from a student of yours from ISWBM, Protoy Ganguly. And he has asked that if we have the statistics on everything, why is there no execution or implementation of plans on the part of the government in consideration of the Indian variables?
I think that that's not fair to the government. Government is trying. Government is trying. Dr. Saha had said so many things. Aquifer management. How they are doing it. We are learning. We are learning, and government is trying. But remember one thing: individually, what are we doing? Individually, we should also try. It should not be a blame game. It should not be a blame game. Government is not trying. No, I'm sorry to say no. Government is trying very, very hard. But what are we doing? Exactly. And over the years, the water sector, is improving. The water sector is improving. But then we individually, we are more than 130 crore people. Tell me how aren't we wasting water in the city? 40% of the water is being wasted in the city. It's wasted in our houses. It's wasted on the street. And that's because of our individual fault. Okay. And we are, say, for example, rainwater harvesting, artificial recharging, it's coming up in a big way. It's coming up. People are trying to understand. They're learning, groundwater science is coming up fast, very fast. And Presidency University is one such university which is coming up very fast in this area. So therefore, we are individually learning. Eastern India, I think from groundwater point of view, from hydrogeological point of view, we were latecomers. But fortunately, Presidency University, they have come up, and this seminar is one such evidence that they are coming up, and they're going to come up very fast. So individually, we need to do. University, from academic points of view, we need to give importance to this subject. The government is trying, everybody is trying to improve the water sector. And I'm pretty sure, I'm very, very confident that this water sector is going to improve. The groundwater in the city is going to improve. The groundwater in West Bengal is going to improve. The city municipality, what are they doing? You know that. They are cutting down on groundwater now. They're trying to, treat water. And do you know what is the cost of this water treatment? It's a high cost water that we are getting it for free. And still we are wasting that. So groundwater, stress is, the government is trying, at least our municipality, Calcutta Municipal Corporation, is trying to reduce the stress on the groundwater. And when you start trying this, the results would not be immediate. It would take some time. It would take some time for the aquifer, so that the groundwater comes up. And that could take, we had taken more than 70 years, from 1955, what we have done to our system, and now overnight it cannot go back to 1955. So for
Right.
Kolkata, if you look at Kolkata, from a closed groundwater system, again going back to an open groundwater system will take a long, long time. So you have to give that time. Government is trying. We individually should try. I think I have answered the question.
Yes. Sir, can you suggest this? This is a question from Rinki Kumarin from University of Delhi. She has asked that, can you suggest any particular way to reach to every single person or a family in the rural areas, especially to educate them about the sustainable use of the groundwater resource?
Yeah.
Can you suggest something?
We could, we should use our local government. You should use our local NGOs. You have in every village, you have systems, you water user committees, try to build up water user committees. And, if the Central Groundwater Board, they are trying to reach to these villages. They are trying to educate people on this groundwater resources, on water resources on the whole day, and especially on groundwater. Central Groundwater Board is trying to do that. They are doing it. Every year they are having programs in the rural areas. I know that. Even in the urban areas, even sometimes they're going down to the rural areas, to villages, and they are conducting, I think the State Water Board is also doing it. Dr. Ghoshal was a part of the State Water Department before he joined. I think he also did some of these, work in the villages. So everybody is trying, again, I would say. So, but again, we need to use, the panchayats are trying, the local bodies are trying, everybody. So that's, I think, we need to do, and we are doing it. Local bodies are trying, the NGOs are trying, to reach to the farthest of the people. NGOs are reaching to the, down into south in Sundarban areas, where it's pretty difficult to go. But, we have a lot of NGOs working there.
And like you said, that we have to know our job. It's not a blame game, and it's not. We cannot blame others. We have to do our own responsibilities properly.
Correct.
Okay. So next question is from Manos Ranjan Shai from Nimapodo College in Puri. He has asked that, what is the basic method for sustainable development of groundwater in Puri coastal areas, mainly Ostorongo and Chilka, because this area is contaminated by iron and arsenic?
That's a difficult question for me to answer, because it's such a local problem, and I have really no idea. I haven't worked in this Puri area, but I'll tell you one thing, from my West Bengal perspective, iron is a big problem everywhere. Even in South Bengal Basin, iron is a big problem. We have high iron. And arsenic is also a big problem. Now, for this arsenic, we need to know where the arsenic is. Mostly it is in the shallow aquifer system. And then we need to find out where you have this paleosol. Even in Puri district, if you have it over there, if you have arsenic in groundwater, if it is a natural arsenic, geogenic arsenic, and then you need to, look into these paleosols, where there are paleosols. If you have paleosol, look below paleosol. Do you have a brown sand? If you have a brown sand below paleosol, this paleosol, if you look at the paleosol, it's very, very tight. It's impermeable. Water cannot penetrate. So even if you have a shallow aquifer, which contains arsenic, and if you have a paleosol at the floor of this arsenic, floor of this aquifer, then the arsenic water is not going to flow down. And if you have brown sand is oxidized sand, and in oxidized sand you do not have arsenic. But if you have gray sand all over, and if you have a shallow channel, if you have a channel deposit of gray sand in the shallow level, it's pretty sure that you are going to get arsenic. And if the paleo channel is missing, or you had a Pleistocene channel, or the Holocene channel was deep enough to wipe off that paleosol, this Pleistocene paleosol, then you could have arsenic from the shallow aquifer. infiltrating because of pumping, it moves down into the deeper aquifer. But generally, if you have a paleosol, if you have a brown sand, and then if you have a gray sand, then the brown sand and gray sand in this part of West Bengal, in this part of the Bengal Basin, in South Bengal Basin, is generally arsenic free.
Right.
Yes, sir. Yes.
The next question is, sir, from Abdur Rahman. He's from CSR NGRI, Hyderabad. He has asked that, is it possible to use most of the fresh water of perennial rivers to recharge the overexploited area in the northern India before going into the ocean?
Remember one thing. If you want to recharge through river system, you can do that. But then again, the rivers are polluted. So therefore, if you recharge the aquifer, even without treating that, what you are doing is you are putting that polluted water into the groundwater system. And remember one thing, groundwater has a very low velocity, the flow is laminar, and so in case of a laminar flow, and if you put in any pollutant, it is very, very difficult because it's going to flow in a straight line. And you are not going to have dispersion, and the concentration is going to remain constant. So therefore, you have to be very, very careful again into recharging, directly pollute surface water into the groundwater body. You do not know what you are going to do. You might jeopardize the entire groundwater system quality-wise.
Okay. Sir, next question is from Shamol Shingho, Assam University, Silchar. He has asked you to explain a bit regarding the supply side and the demand side measures of groundwater management.
The supply side it's very simple. The supply side is very simple. If you look at, you need to increase your supply because your population is growing, your demand is growing, and with more population, you need to have more food because everybody is hungry. You have a hungry mouth and you have to feed. So you need food. So for that food, you need to have more water because to grow food, to grow crops, you need water. So therefore, you have to increase your supply. So, increasing your supply there, as I said, there are so many ways. I don't know whether you can see it on the screen now. You can construct check dams, you can have rainwater harvesting, artificial recharging, you could reprocess your wastewater. That's very, very important. Huge amount of wastewater is coming out from our industries, from our homes. Can't we utilize those water? Can't we have utilized the water that is, utilize a part of the wastewater, which is not black water? Can't we utilize that water back into our home? Can't we use that, that wastewater that is coming out for car washing? So we need to think about that. This is how you can. So then you could also, but it's very costly. So desalinization of brackish water, Israel is doing it. But again, can we, because it's a huge cost, can we pay for that? But again, that's another way of, increasing your supply side. And then finally, you could relocate water from one use to another sector. That's another way. Now you're coming up with a zero water discharge concept in industry. That's very, very important. Industry should need to come up with this zero water discharge or minimum, everybody calls it zero water discharge. I would say a minimum water discharge. Try to move to a zero discharge so that whatever is there within your industrial premises or your factory premises, that water should stay there so that you cut down on the fresh water that you are taking every day. Even, on village-wise, you can also try something, so that your village water, the wastewater, when we're pumping out a hand pump, the water should not flow into a river or to some canal, and the water flows out of your village. Try to put that water back into the aquifer system, back into a pond, so that you could artificially recharge that by some mechanism. There are means and ways of doing that, so that the water remains within your village. Okay, so these are the important things. Now for demand again, you need to increase, as I said, water productivity. So cut down on your demand. When you cut down on your demand, when can you do it? You can when you waste less. Because wastage is a big problem. Productivity is a big problem. Productivity both in the agricultural sector and the industrial sector. We use flooding means of irrigating our land. Can't we get rid of that flooding mechanism even in the eastern part of the world where we tend to have more water? Okay, and then finally, I would talk about appropriate pricing policy. At least in many of the cities, at least in Kolkata city, I know, and in West Bengal in general, the water is free. So if you have to pay for your water, I'm sure your demand would be less. Because you are paying for electricity, your demand for electricity is less. You are switching off your lights and fans, your ACs. You are not put now. If you have a free electricity, then all the ACs would be running in 24 hours. Now, that's what is happening in the water sector. And then finally, I would say, conjunctive water use is very, very important. I think I repeated the supply and demand management.
Yes, sir. Sir, one last question I would like to ask you. This is from Mr. DC Jhadia, NIT Raipur. He asked that you have shown in one of your water table maps in your PPT that there is no influence of the existing river on the water table, Contu. So what is the reason behind it?
And the reason behind is, I think it is because Kolkata's water is under confined condition, and the river system, the Hooghly River, below that you have a thick Hooghly River. Okay, all over. So therefore, you do not have any of these impact on the. But if you Dolly's Nala or the Adi Ganga channel, you have direct impact of water, sewage water moving from the this Dolly's Nala water moving directly into the aquifer system. But at least the main river Hooghly, you do not have any connection with the groundwater of Kolkata, but Tali's Nala or the Adi Ganga River has a direct connection because the aquifer system over there, over somewhere around a 500-meter stretch, on either side of Tali's Nala, you're going to have, this unconfined, or less than 500 meters or so, you're going to have this unconfined. So what is important that we need to trace this unconfined aquifer in Kolkata, and that has not been done. So somebody could do that work.
Okay. So because of time constraints, we cannot take any more questions. So you can send all your questions through WhatsApp group, and we'll forward that to sir so that he can answer all. Thank you so much, sir. Before closing the session today, I would like to thank both the speakers for their wonderful and informative presentation. And I also want to thank all the participants for their patient hearing. I learned a lot from these two lectures, and you all have possibly learned a lot too from the sessions. Hope to meet you tomorrow at the same time. And please keep an eye on your WhatsApp group where the schedule will be sent to you soon. Goodbye. Have a good day. Thank you so much.
Thank you, Utsav.
Thank you, sir.
And Aditya. And all the students.
Yes, sir. Thank you. Thank you, sir.
Thank you, sir.